remove this also. It's working? Okay, I hit the controls also, that's good. I now figured out how it works much better now. Okay, cool. Guess let's get started. We're going to continue where we left off yesterday. You wanted me to start memory performance attacks, and we started. We were kind of in the middle. I'll just jog your memory until we get to that point where we stopped, and then we'll continue from there. Does that sound good? Okay, cool. So we were talking about memory quality of service. Okay. Yeah, this is, I think, the third time I'm showing this picture with your timing, but this is such an important picture. And we were talking about how abstractions are improving productivity, but we need to break through them if we actually have problems. And I was mentioning that today we always have problems, basically. There's no system that you can build without any problems: performance problems, energy problems, scaling problems, cost problems. And I think you will need to, as computer designers, cross the abstraction layers going into the future much more easily than people in the past may have been used to, let's say. Although good people always cross the abstraction layers. They built the systems, they actually pushed the field forward by actually doing research across the layers and doing products across the layers. But now I think the flag is with you, let's say, going into the future. And I think knowing how to do this is actually useful for you in many areas, as well as we discussed in the course logistics yesterday. Okay, I'm going to skip this one. We talked about that. We were talking about multi-core systems where some caches are not shared, some caches are shared. Memory control is definitely shared. There may be multiple memory controllers. This is an old multi-core system, actually, from 2006. In modern systems, you actually have many memory controllers and many more cores also. So systems are scaling, basically. But the problem still remains, the problem we're going to discuss, and we have started discussing. And these were some examples of multi-core systems, older and newer, as you can see. And they all share that problem, basically, which is the interference in the memory system problem that we have been talking about. Okay, just to remind you, what we want is we want to get scalable performance, linearly scalable performance, let's say, as you increase the number of cores, right? But today, what we get is something much lower, let's say. And this is one example of this. This is another way of looking at scaling the performance in terms of slowdowns. Ideally, you wouldn't slow down at all, right? When you're running multiple cores. When you're running multiple applications, multiple cores, every application runs as fast as it would run if it were running alone on the same system, right? But that's not the case today. As you can see, these are experimental results from real systems 15 years ago. Today's results, I think somebody needs to gather them and look at them. That's good to do, maybe, but it's not very new to do, let's say. Although it will show you how much progress has been made in the last 15 years, potentially, right? And I believe today we're still not as good as we should be. Basically, we cannot provide predictable performance to different applications that are running on the same system. We have become better, as we will discuss in the interference lectures later on, maybe 10 lectures later, but we're not as good as what I think we should expect computers to do for us, let's say. So you can see that there are unfair slowdowns when you run these two applications together. And it doesn't matter whether you change the priority of the application in the operating system, because the operating system just schedules the applications to the different cores, and they run without any interference from the operating system later on, basically. Priorities matter when you actually have more threads than cores that are ready to be scheduled. Then the operating system tries to prioritize based on the information that you give as a user. Okay, we call this the memory performance log, and we were talking about these questions. Why do the applications slow down? Why is there disparity in slowdowns? And can you fix the problem? And this was another way of talking about the questions, basically. Why is there any slowdown, disparity in slowdowns? What if you don't want that disparity? Or what if you want to control that disparity, let's say? Maybe you don't want it sometimes, maybe you want it sometimes. If you don't care about, for example, the performance of MATLAB, no, the other one, DCC, you don't care, right? It's okay. But in many cases, you may care. Okay, we talked about why is it important. Things are being consolidated more and more on multi-core systems with multiple processing agents, let's say. And that's true all across the field, basically. There's a push for efficiency. And that's good, I think. Efficiency is good in general for energy efficiency. And that we discussed that. That's an important concern going into the future. And we want to mix different types of applications, those requiring some strict guarantees, less strict guarantees, and maybe no guarantees. And all of them will be running concurrently. And to be able to do that in a nice way, you want the system to be really controllable. At the same time, high performance, right? If high performance is not there, then controllable is easy, as we discussed, right? You design a 1,000 core system, you just run one application, underutilize the system terribly. That's not high performance and also not energy efficient in the end. Okay, so this was the slide we finished with yesterday. This was where the experiment was done. I showed you the results for MATLAB and GCC, right? MATLAB was running in one core, GCC was running in another core, and they were not sharing caches. They were sharing some interconnect, but probably not. The sharing over there was not that bad, but we nailed down the problem to be the memory controller with our experiments. You can read the paper also. And the memory controller was basically prioritizing the requests of MATLAB over GCC's pull request, let's say. GCC once in a while generates requests. MATLAB generates a lot more requests, and the memory controller was unfair to GCC. Of course, when I say unfair, it's always with some definition of fairness, right? And definitions of fairness are always difficult to do in general. Well, in general, actually, not in computing, but also in economics, etc., right? And social sciences too. But assuming that the fairness is, let's say, equal slowdowns in this case, if you want to achieve equal slowdowns for equal priority applications, then this is clearly unfair. If you want to minimize the maximum slowdown, maybe this is also unfair. Maybe there's a better way of minimizing the maximum slowdown that any application experiences, right? Probably maximum slowdown should not be 3.07 like we saw for MATLAB. Make sense? You can also come up with other definitions of fairness that are not at the application level. It could be, for example, every cycle I pick from a different application when I schedule a request. That's another definition of fairness. That's a more local definition of fairness in the memory controller, which may or may not have meaning at the higher level application level, right? I gave you earlier an application level definition. Slowdowns should be equal. You could argue whether that's good or bad, right? Assuming equal priority applications for now, of course, right? Or maximum slowdown should be minimized as much as possible and should not be higher than some amount. That's another definition. Or you could be more myopic, let's say, and more localized and say DRAM memory controller should be servicing in a round-robin manner different applications. Yeah, that's another definition of fairness, clearly, if you look at the local thing that's happening. We will see that that's not fair, actually, from a slowdown perspective, application level perspective. But we will probably leave that for the interference and quality of service lectures. But you can start thinking about different definition of fairness right now. Okay, this is where we ended in last lecture. Hopefully you guys remember. I can see people nodding heads. That's good. So we ended in last lecture here because I don't think we fully explained what was happening, why the memory controller was designed to prioritize MATLAB over GCC, right? We didn't really nail that down. If you really want to understand why the memory controller is designed to do this, or what the memory controller is doing, you should really look at what's happening in the DRAM banks. And that's what I was going to do, basically. I was going to talk about these DRAM banks and how they operate. Okay? Okay. So I think this will be useful for future lectures on DRAM also, but we're going to see this picture multiple times. A DRAM consists of basically composed of multiple banks, as you can see over here. And each bank is a two-dimensional array of cells. Each cell is a storage unit like we saw yesterday. Not a storage unit, but a capacitor and access transistor. It's called the memory cell, right? Now, we're abstracting them away. We're not showing them over here. And this is a cartoonish picture, clearly. And this view of a bank is an abstraction also. Internally, a bank actually consists of many subarrays. This is a big array. Internally, you have many subarrays of cells and other structures that enable access to subarrays and cells. And we're going to see that later on in lectures. So if you look at memory, at a high level, you may think of this, at an abstract level, you may think of it as a monolithic array, right? You go one level down, it consists of multiple banks, which are different arrays. One level down, this bank consists of subarrays, smaller arrays. If you go one level down, subarrays actually consist of mats, and I think that's where it ends. But you could keep doing that, basically. The goal is really to reduce latency as much as possible, because one single monolithic array takes much longer to access, right? As opposed to breaking it down into multiple parallel arrays. And also, one single array may not provide you the bandwidth you need if you want multiple parallel requests, it can happen with the multiple banks concurrently, right? If you had a single array, we will see that again in later lectures, but it becomes difficult to actually parallelize the request in the single array. Okay, so let's take a look at how this bank operates for our purposes. I'm giving you some information that will be useful for the future also, hopefully. Okay, so there's a row buffer in DRAM that basically holds the data of a row that's accessed. And this is needed because you need to sense the row. So this has to be there because these are called also sense amplifiers in DRAM. And row buffer initially is empty. It contains nothing. Now, if memory controller wants to access some address, an address is encoded as row and column numbers, row 0, column 0, let's say. The memory controller first needs to issue an activate command to DRAM saying, DRAM, give me this row, or open this row, activate this row. And DRAM obeys that command. Remember, DRAM is the slave, and memory controller is the master, let's say. That's how it is because that's how it was designed. DRAM cannot do anything without the memory controller today. So the DRAM opens the row, places it in the row buffer. Right? Now row 0 is nicely there. Any column that you need to access in row 0, you can access from the row buffer. So you don't need to activate it again. Right? Make sense? So you can think of this row buffer as a small cache also that caches the last activated row. Okay. Now, if the memory controller wants to access column address 0 from this row, it basically sends another command saying, I want column 0. Column 0 could be a cache line, for example. And basically, column 0 from the row buffer gets multiplexed out, and the data gets sent to the memory controller. Okay, so that's one read that happens. Now let's take a look at another access. Now, if the memory controller wants to access row 0, column 1, because the processor requested it, and this is the state of the row buffer, that means that the access hits in the row buffer. Row 0 that we want is already in the row buffer. It's a hit, meaning that we don't need to activate the row again. We just need to send the column address, and the column address gets data in the row buffer. Appropriate column in the row buffer gets read and multiplexed out of this column mux. Now that's much faster, of course, as you can see, right? Okay, now let's take a look at another one. Row 0, column 85. There may be many columns, clearly. We will see exactly how many later. Don't worry about that right now. So we get, well, it also depends on the DRAM chip, so it's not that fundamental, but it could be thousands of columns. So you get a hit in this case, again, because it's row 0. And again, the access is fast. You get the idea, basically. If you keep accessing row 0, your accesses are fast. But if you want to access, let's say, row 1 at this point, the memory controller needs to do a lot of work. Let's say, first it needs to basically, this is called a row buffer conflict. The row that you're looking for in the same bank is not in the row buffer of the bank. In fact, there's some other row in the row buffer of the bank, which means that it's conflict. So you first need to prepare the bank for activation. That takes some time. We will talk about exactly how that is. You will need to pre-charge the bit blinds so that they can sense the next row, let's say. And then you need to activate the row that you're looking for, which takes some more time. And then now that the row is there, you ask for the column that you're looking for. So clearly, this takes a lot more time, this row conflict, right? Now we know what's going on underneath. And you can appreciate someone may design a memory controller that tries to maximize the row buffer hit rate, right? Yes?
Wouldn't the accesses to row 0 hit in the cache, or is the row way larger than a cache block?
Oh, yeah, that's a very good question. So a row is usually way larger than a cache block. A row can be, as you will see soon, 8 kilobytes, whereas a cache block is usually 64 bytes, 128 bytes. If you're IBM, it's 256 bytes, maybe. Yeah, that's a good question. Okay. Okay, so now yes, one more question.
So the columns here, are these bits or words, and do they get serialized out through the multiplexer? Or
yeah, so don't worry about that as much at this point. Columns, if you look at a chip itself, it could be 32 bits. It could be 64 bits. It depends on the chip, basically. But you normally put multiple chips together in DRAM, as we will see in later lectures, so that you get a cache block out. Well, you get columns could be 8 bits also, actually, depending on the chip, basically. but they're normally put together in multiple chips so that you get a cache block out in multiple bursts. We will see that when we talk about the DRAM. That's why I didn't want to go into that detail, but that's a very good question also. Think of this as a cache block for now. In the aggregate module, it's okay to abstract this as when you're reading a column, it's a cache block. But as you go deeper, of course, you will see that it's a different story. But abstraction, I think, still holds. Okay, good questions. Now I'll move on. Basically, the reason I'm describing you this is because this leads to some design choices in the memory controller that would lead to a part of the unfairness. Okay, now I already told you, right? If you were a designer and if you'd see this, what would you do? You would try to maximize the row buffer hit rate, right? With your scheduling policy in your memory controller. If you have accesses that go to row 0, you would schedule them first so that you get the accesses done quickly, and then you would switch to row 1, for example. And that's exactly what memory controllers were designed to do. Because a row conflict access takes significantly longer than a row hit access, controllers at the time, they still do. Currently, they still take advantage of this fact, but since it's been 15 years after this research, clearly they do other things today as well. So commonly used scheduling policy is called first ready, first come, first serve. It's a mouthful. But basically, they among all the requests that are in the memory request buffer of the controller, and there may be many because memory is the bottleneck, as we discussed, right? Many different cores can be sending me their requests. The prioritization order looks like this. Row hit requests are serviced first, and all else being equal, meaning among the row hit requests, or if there are no row hit requests, among the row conflict requests or row closed requests, older requests are serviced over younger requests. This kind of makes sense, right? If your goal is to maximize data throughput, it's not a bad policy, let's say. So the policy tries to maximize DRAM throughput. But later, we will also see that you should do other things to maximize DRAM throughput when we talk about machine learning-based memory controllers, for example. But this is a nice, simple, human-driven heuristic that works, let's say. The problem is that multiple applications share the DRAM controller, and in multi-core processors or multi-threaded processors, and memory controllers are designed to maximize data throughput. And maybe it's okay in a single core where you're running single application, single thread, right? But if you're running multiple applications, you become unfair to some applications. And both of these properties, the two prioritization policies actually are unfair. Row hit first and oldest first. And they're unfair in different ways, as we will see. So row hit first unfairly prioritizes applications with high row buffer locality, right? If an application keeps accessing the same row over and over, and then moves to another row, keeps accessing that row over and over, and then moves to another row and keeps accessing that row over and over, it has good row buffer locality. Meaning, if you do the right thing, it will keep hitting in the row buffer most of the time, right? So these are threads that keep on accessing the same row. Other threads that are more random access, let's say, unfortunately, are not prioritized by this policy, right? Because they keep accessing different rows. They don't have to be completely random access, of course. They may access a couple of things in the row, and then they may move on to some other row. Right? They still have lower row buffer locality. And the oldest first policy, prioritization order, also unfairly prioritizes applications. Oldest first may sound fair from an age perspective, but it's very unfair from an application intensity perspective. Because think about an application that is very intensive, meaning in a given microsecond, let's say, it generates 100 requests to the DRAM. Another application in a given microsecond generates 1 request, just like the picture I showed you earlier. Which applications' requests are naturally older to the memory controller? The application that keeps generating many requests, right? 100 requests in a given microsecond. So that poor 1 request from GCC will get delayed because of this oldest first policy, because some other application keeps generating requests that are naturally appearing older, right? That's how it is. That's how age works, right? If you keep injecting things at a constant rate or some rate, or if you keep injecting more things that are those are going to be older than someone else who is injecting very few things. Okay, so hopefully that's clear, right? Yes.
What range of?
I cannot hear you very well. Maybe it's not working.
what time difference are we talking about by optimizing for row buffer hits?
Okay, we will. Okay, that's a good point. I said 2 to 3x. Yes, I think you want basically what's the nanosecond. Let's say. I mean, you can think of a row buffer hit is maybe 30 to 50 nanoseconds, and row buffer conflict maybe 60 to 120 nanoseconds. Let's say, depending on the DRAM design, etc. So it's significant, basically. It's on the order of 40. Let's say 40 to 50, 60 nanosecond difference. If you think about a processor with 4 gigahertz clock frequency, it's 250 cycles, right? That's a lot. You could do a lot of work in 250 cycles. Okay, so basically, this unfairness is not good from a quality of service perspective, but it also makes DRAM controller vulnerable to denial of service attacks. Whenever you have a quality of service problem, you should also think of it from the malicious perspective. Whenever you have some, let's say, reliability or robustness problem or quality of service problem, someone can exploit it. It's always good to have this mindset. And I like thinking of systems this way. Like when we started out with memory controllers, we were thinking this way also. It's always good to think of systems this way, right? Because in the end, security perspective is actually really critical, right? Someone can exploit it and maybe may render your system, I don't want to call it useless, but too slow to actually deal with. So you can write programs to exploit this unfairness. And that's what we essentially did in this work. Basically, after realizing the problem, we wrote this program. It's called Stream. Actually, we borrowed it from a benchmark suite that measures memory bandwidth in microprocessors. We modified it, of course, for our needs. But basically, at the high level, this benchmark does something like this. It initializes 2 large arrays, A and B, and it copies the values in B to values in A in a streaming manner. Consecutive addresses are accessed consecutively, right? So it's sequential memory access. As a result, it has very high row buffer locality. It's very memory intensive because we make sure that every access is a cache miss. You can see that index is J times line size over there, cache line size here. Okay, so we also wanted to control this. We wanted to have a similarly intensive application, but with a different access pattern, meaning a random access pattern. Okay, I mentioned that. This benchmark does essentially exactly the same thing, but it copies array B's elements to array A's element in a random order, meaning it picks random elements. Elements in random locations, I should say. As a result, it has very low row buffer locality, and it's similarly memory intensive. It should be, because every access is a cache miss again. Yes?
So on the left, it says 96% hit rate, but in the code, you access every access in a different line, right? Shouldn't this produce a low locality?
This is how, in terms of row buffer. Remember, row buffer is large, 8 kilobytes. It consists of many, many cache lines. So basically what you're doing with this workload is you're streaming through the row buffer. Your cache hit rate is terrible, no question about that, because we're making sure that you're missing in the caches of the processor. But this is a very nice pattern for streaming pattern for the row buffer. Makes sense, right? Okay. This here, the cache hit rate is essentially the same as this one, but row buffer hit rate is close to 0, as you can see in the measurement over here. 3% is the measured value. Because sometimes random is not random, right? You can by luck get to the same same row buffer. Okay, makes sense, right? I mean, you can also question basically, is this the right measurement? This is an abstraction also. This is not exactly the benchmark. You can find the benchmarks online. But if you actually put this random function call over here, you're really perturbing the measurement, because that random function call takes a long time. So you really need to pre-initialize an array and then do the copying such that we're going to measure the time it takes to execute this loop versus this loop. And the only difference we want between these loops is really the copying performance, right? Not the random run number generation performance. So keep that in mind. Whenever you do measurements, you have to equalize what you're measuring in both cases. Okay, cool. So let's take a look at these applications. What do these two things do? So I think you may have guessed it. Basically, I'm going to show you the stream and random applications. I'll go to call them T0, T1. And this is a memory request buffer where we've extended our picture with a request buffer in the memory controller. And let's assume that stream application generates one request and row 0 is open. Now let's take a look at what happens. Memory controller serves that request, and then a request from random comes, but memory controller is busy servicing the request here. Another request from stream comes. When this earlier request ends, the second request from stream gets prioritized over the request from random, because this hits in the row buffer, this misses in the row buffer, right? And then basically this keeps happening. Random keeps generating requests at almost the same rate as stream because we designed it to be that way. But stream keeps getting serviced because its accesses keep hitting in the row buffer, right? And random doesn't get a chance until stream stops accessing row 0. If you have a bad memory controller. Some memory controllers have a timeout policy saying, oh, if I have serviced from the same row for I don't know how many cycles, I'm going to close the row. It's not fair also. Those timeout policies are actually pretty bad in terms of fairness. But basically, with a row size of 8 kilobytes and a request size of 64 bytes, which is the cache line, you have 128 requests of stream service before a single request of random, right? Assuming the memory controller behaves the way I mentioned, right? And it does in that case, yes.
But you said the row buffer was smaller than the row size. So the memory controller only takes into account like the row index or what's in the row buffer?
So row buffer is not smaller than the row size. Row buffer is exactly the same as for 8 kilobytes, basically. No, it's the same size. And DRAM, it has to be, as you will see in later lectures, because you're really sensing the entire bits, you have to have exactly the same size row buffer. Yeah, if it was smaller, then yeah, there would be other equation over here. Yes.
Is there some out of order execution in the CPU because the request from T1 has not yet satisfied, but there are multiple requests queued there?
Oh, okay. Yeah, certainly there's out of order execution. Basically, the CPU is keeping on executing different loop iterations, right? Yeah. With an in-order CPU, you may not experience this as much, yes. If the CPU stalls on the first request and waits, and it doesn't have an instruction window that's large enough, yes, you're right. But modern CPUs are all out of order and they can do this easily. But that's a good point also. That's good, people are thinking. Okay, so hopefully this is clear. This is one reason why stream denies service to random. Well, in this case, this may be the only reason because we've equalized everything else, right? Intensities are similar. But this is one reason why MATLAB denies service to GCC. There's another reason, which is the oldest first reason, which I didn't demonstrate here, right? Because MATLAB is also much more intensive than GCC. But this particular example was to show the effect of the row buffer. Okay, so actually we did the measurements with this controlled experiment also, stream and random. And you can see Intel Pentium D. That's the name of the processor that I didn't remember. You can find out. This is Intel's first multi-core processor. They literally took 2 single-core processors and put them together, I think. Of course, they did something in the memory system slightly so that they can work together nicely, but that's essentially it. That was an easy way to get into multi-core, right? Okay, so you see these based on the measured results, stream slows down by 18% and random slows down by 2.8x almost. So that's as expected also. Okay, and so we actually did it for many different processors. Well, maybe 2 more different processors we had access to, let's say. There were not that many multi-core processors, at least that was easy to access at that time. And when we talk about multi-core, you will see that first multi-cores were actually done by IBM and Sun, but those are expensive systems. Intel and AMD are clearly more general purpose. Well, those other ones are also general purpose, but cheaper systems that we can use. But the problem exists in all of those systems also. Everybody acknowledges this at this point. Okay, and we actually ran these applications, ran stream. We basically called stream the memory performance hog because it's intensive. It's also has very high row buffer locality, which is favored by existing memory controllers for good reasons, as we discussed. Stream denies service to any application that's run with. Virtual PC was Microsoft's virtual machine. So we wanted to demonstrate that this is actually a problem with virtualized environments as well. Okay, so this becomes a bigger problem with more cores also, actually. As you can see, this is a simulation experiment we did, but you see similar results. You see 4 core. In this case, you have 4 cores, 4 applications, One application slows down very little. Another application slows down by 8x. And some applications like video encoding, decoding may have some service requirements, right? So these are applications from the spec 2006 workload suite. This is a quantum computing simulator. This is a network simulator. This is clearly video encoder, decoder. And I think this is a genome sequence analysis workload. Okay, so basically, I will argue that this just should not happen because it makes the system vulnerable to denial of service, as we demonstrated. It makes the system unable to enforce priorities between different applications. As a result, unable to satisfy service level agreements. If you're doing cloud computing, for example, if you have a service level agreement saying, this is the performance that I guarantee you, you will not be able to do that by arbitrary collocation of different applications in a multi-core machine, right? Or if you have a service level agreement with your user, like maybe it's not specified, right? I have a service level agreement with this thing, and if it doesn't satisfy me, I will not buy it again, right? So, and also at least low system performance. This may be interesting also to think about, right? Actually, this denial of service leads to some cores being utilized badly. So you remember the MATLAB versus GCC example. MATLAB is making progress. GCC is not making progress a lot, right? So as a result, you're not utilizing the GCC's core very well. As a result, this also hurts system performance significantly, as we showed. Not always, but usually this sort of bad denial of service actually hurts system performance. Does that make sense? Ideally, you would like to utilize all of the cores nicely. In fact, if you look at this picture, libquantum is a very heavy application. It's also streaming. It's naturally very slow. So you're prioritizing it in the memory controller. As a result, some other application, this looks like GCC actually in our earlier picture, OmnetPP, which is not very intensive, which has only one request once in a while, but it gets stuck. That request gets stuck, so the core cannot make progress. That's essentially the core that you really want to prioritize, right? It has only one request once in a while. If you prioritize it, its core will keep running nicely, right? It's really a fast application to begin with because it's not memory bound as much. So what we're doing is really with the policy that is implemented in these processors at the time, you're really prioritizing the wrong applications to improve performance. You're prioritizing this already slow applications to begin with. Right? So that's the wrong choice if you want to optimize for system performance also. So it's very interesting. It may be the right choice if you have a single thread, right? As we discussed, maximizing DRAM throughput, but it becomes the wrong choice because of this interference between different applications. Okay, so hopefully this is clear. Basically, in the end, you have an uncontrollable, unpredictable system, and there's no way to control it basically, other than descheduling applications. Okay, I want OmnetPP to run nicely. I'm not going to run it with anybody else, right? And that's terrible, of course, as you guessed. So there are many demonstrations in the paper and other papers also. Okay, so now let's talk about solutions, unless people have questions. Okay, everything is clear. That's good. Okay, so basically, how would you solve the problem? What is the right place to solve the problem? And yeah, maybe I will. Okay, any thoughts? How would you solve the problem? Yes. Yeah, exactly. I think that's a natural way to think about it, right? Better policy in the memory controller. I agree.
You do it on like the program level, like it's unreliable.
Mm-hmm.
You change the policy, then the programmer.
Exactly. Yeah, let's talk about this one. I asked the programmer. Yeah, basically, you cannot even do it at the programmer level, right? Because you optimize only one program. You have no idea who you're running with, right? Yes. Mm-hmm. Mm-hmm. Yeah, how would you determine those quotas? That's the hard part. But yes, I mean, there may be something there. I agree. Maybe operating system tries to figure out which applications run nicely together, right? And then just schedules them together. Assuming operating system gets the right information from profiling, that could work. Quotas may be harder to determine. But I think quotas, if you can determine them, they could be a good way of enforcing predictability in terms of performance, right? As we will discuss later. Mm-hmm. Yeah, maybe. But someone needs to communicate those. Yeah.
I think you can do something to, I think you can base the quotas on the computation to memory ratio. Because if the goal is to use your cores all the time, right? And some cores, like you said, only need to take one piece of data and perform 1 billion operations on it. So I think you should optimize it that way, so your cores are always computing something.
So that's, I think, one way of automatically trying to estimate how much service each application can get. And we will see similar approaches when we talk about memory quality of service techniques. Yeah, I think some of that may work actually if you can do it rightly. Yeah. Machine learning to manage this interference. You'll need to design it. I don't know how at this point. Can you press the button? Yeah, maybe others also can hear.
Wasn't there an article that said that they use machine learning with memory controller to improve the performance?
Yeah, that was what we discussed yesterday, and we're going to see more of that. But that was just performance. That didn't look into interference. But I think, granted, you're right. There have been works that show that you can use machine learning to manage the interference also. But it really depends on how you do it. So yes, at the higher level, yes, but the devil is in the details of how you do it. Yes, yeah.
Yeah, I just wanted to say that I think machine learning, like using machine learning to solve a security issue, is always dangerous because it has been shown that you can always manipulate machine learning to do exactly the opposite of what it was supposed to do.
Possibly. Depends on the machine learning approach, I think. Yeah, I think neural networks are shown to be very, very unreliable from that perspective. But reinforcement learning is probably better. Yeah, I think people rely too much on neural networks these days, let's say. There are other approaches to machine learning, like reinforcement learning, that are, let's say, harder to trick, and people are not attacking them. People should be attacking them also, I think. But good point, I think. Yes. Yes.
Would it be possible to maybe increase the size of the row buffer? The row buffer, so that it can take multiple rows at once instead of just one.
I see. So basically, create multiple rows. That idea has been proposed also many times, but it's very costly. Yeah, row buffer is a very costly structure. You will see that when we talk about DRAM more. This row buffer is there because it has to be there. If you keep adding one more, it increases your cost significantly. And then you also still need to manage those row buffers, right? Who gets those row buffers? Does every thread have a separate row buffer to itself? If you have 1,000 threads, then it becomes really, really prohibitively costly. Yeah, but these are, I think, good ideas that you're throwing out. I think people throw out system software. Nobody talked about compilers. Compiler and programmer, I think, cannot solve the problem here because they see only their own application, right? So you can easily remove that. System software can potentially solve it because it sees all the applications that are running. And I think it has to be involved in some solution at some point, as we discussed yesterday, right? Hardware, I think, as you mentioned, this is a good place. And as the machine learning approach is mentioned, that's also hardware, right? You need machine learning in the hardware. How about DRAM? I think that was your approach with the row buffer, adding row buffers in the DRAM. Any modification that you do in DRAM is going to be costly. So that's the downside over here. Circuits, I don't know. Quality of service aware circuits, maybe. I don't know how to do that, yeah. But basically, I think there's a wide variety of things that you can do. What seems most feasible is memory controller and system software to me. And so both of those approaches have actually been studied in literature, and you will see those soon. So basically, I think hopefully what we're exercising is really thinking critically and maybe thinking broadly also. Basically, don't dismiss any solution without thinking about it, let's say. Maybe there's some other solution that is missing on the slide clearly, right? That leads to new ideas, potentially. But yeah, all of the solutions that should work really needs to see the multiple applications, right? Solutions that consider only one application will not work in this case. Okay, so that's the paper. And this is, I think, one of the potential readings. I don't remember if it was a required one or an extra credit one, but it's up to you. Now it's easier to review, basically. Now that we've talked about it, it's easier to review. And this is the concluding slide. When I presented this at Usenix Security, it's almost 14 years now, more than 14 years, since it was in August 2007. Basically, this is what we concluded. I think I'm not going to repeat everything, but this introduced the notion of memory performance attacks and shared DRAM systems and unfair. It pinpointed unfair DRAM scheduling as the cause of the vulnerability and showed that this will be a more severe problem in future mini-core systems. And what we did not talk about, which we will talk about later, is basically it provides a new definition of DRAM fairness. Threads should experience equal slowdowns. I think this is a good definition from an application level, but we will also deconstruct it later on. And it proposed a new DRAM scheduling algorithm that enforces that definition. Implementation, it provides an implementation of it also, but implementation is not that detailed in this paper. Later papers actually improved upon this a lot more. And it shows that it effectively prevents memory performance attacks. And you can read the paper and see on your own. And as I mentioned, preventing attacks also improves system throughput. This is not just good for security. If you say, oh, I don't care about security, you should really care about system throughput as well. Because by not utilizing your cores well, you're losing system throughput. And we will see this many, many times later when we talk about quality of service. Yes?
What does equal slowdown mean?
Oh, okay, that's a good question. Now you're getting into the solution. Equal slowdown is basically, as much as possible, you try to equalize the slowdowns.
Then if you have like many requests on one thread and not many on the other thread, then don't we go back to the same problem?
What is the same problem?
Well, the problem is like you have many memory requests on one thread and then just a few on the other thread. So then the memory controller does not, like if you have many, many requests, then you're going to slow down a lot if you're denied by the memory controller or
not
like,
necessarily, right? Because you're taking into when you're computing the slowdown of a thread, you're taking the baseline performance. So if your baseline in the baseline, let's say when you're running alone, you take 10 nanoseconds. If you increase your, if you take 20 nanoseconds when you're running with someone else, your slowdown is 2x, right? Now, let's say a less intensive thread, it doesn't make many memory requests. It takes 1 nanosecond in the baseline. Slowdown will be equal if it takes 2 nanoseconds. Yeah, that's it considers the baseline performance. I think compared to other definitions of slowdown, this is a better one, but there could be a better one also, as we will see later on. Okay, but that's a good point. You're thinking about what slowdown means, right? Okay, so there are other works that I'm not going to talk about right now, but there are further readings that if you're interested, you can look at it. This is a more recent solution, Bliss, as I mentioned yesterday. I'm not going to tell you what it does, and there's a longer version. And we will have a memory controller lecture in this course later on. This was the memory controllers lecture from the last year. So we will see other aspects of memory controllers before we go into quality of service. There are other memory controllers are actually very difficult to design today. They're probably the most complex part of the system, as you will see. If you thought core design was difficult, that's not correct. Memory controller design is much more difficult, actually. You need to consider many, many things. And in my opinion, they're going to be much more important than cores because of the importance of memory going into the future. And interestingly, not many people know how to design memory controllers. So you can have an advantage by knowing how to design them, actually. Okay, so this is a foreshadowing of future lectures to come. We'll have similar lectures like this in this class as well. I will mention one thing, maybe memory channel partitioning. This is an OS level solution. Actually, it's a hardware software cooperative solution. But the idea is to figure out what the applications look like, what their key characteristics are using some heuristics. And if you have multiple memory channels, separate the applications to different channels such that applications don't interfere with each other as badly as I showed you there. That's the idea. It's a heuristic-based method, and I like this idea, actually. And you can see a picture of it also. So we will see this more. I wanted to use this picture also, but this sort of channel partitioning happens in real systems also. Can you see this picture? This is a picture I took at the Zurich airport. I don't remember when, last year probably, or maybe the previous year. Maybe it's not a good picture, but so what's happening here is I'm here, as you can see. There are people in front of me. This is one channel to enter this tram that goes from the airport terminal to baggage claim. But there's another channel over here you can see, right? There's no one there. And that also enters the tram from a different channel, and these are partitioned. You cannot cross this line. I don't know what happens if you cross that line, you will get arrested or something. But basically, only this channel is servicing requests, meaning people filling this part of memory, let's say, or the tram, whereas this other channel is empty. Now you can imagine why this could be a problem, right? There's a load balance problem here. And I've experienced that many times, basically. This gets extremely crowded, whereas half of the tram is empty. Why? Because they partition the channels in a bad way, let's say. Make sense? So basically, whenever you partition, the takeaway is multiple, I think. Channel partitioning is applicable to many things in life. And also, whenever you partition the channels badly, you run into this load balancing problem. You may be underutilizing some channels. As a result, you may be underutilizing perhaps the most important resource that you have, right? Memory bandwidth. So channel partitioning has its downsides also. You need to be careful about it. But I like this real world example. And I always had a problem with it because this always happens amazingly. Whenever I come, well, sometimes you were lucky and your channel is also empty, right? Mostly. That's good. But when your channel is full, why not also offload some people to the other channel, right? And you will see that in our solution, we actually offload people to other channels. You don't basically blindly partition the channels. You have a mechanism to actually offload, use other channels when things are not balanced. Yeah, maybe computer engineers should be making policies in airports. Okay. I hope someone is watching this from the Zurich airport. I understand the reasoning. Sometimes for security reasons, you may want to do this, right? But if there's no one on the other side, then it may make sense to actually go there, right? Okay. Okay. And in Corona times, especially, it's bad to have many, many people together in the same packed tram. Okay, so this problem is more general. Well, not channel partitioning, but the interference problem is actually more general. I mean, I could give you examples from real life and the interference problem also, right? Whenever I try to enter Tannenbar, for example, at a bad time, there may be a group of, let's say, students, 100 of them, who are also trying to enter Tannenbar. And Tannenbar has this revolving door that is a huge bandwidth bottleneck, right? I don't know if it's still being used because I haven't gone there in a while, but that one's a huge bandwidth bottleneck. So everybody goes one by one through that bandwidth bottleneck. And I myself, a small thread, get denied service by, let's say, I don't know, 10 students who are in front of me, which is, I think of them as a group of threads because they're together, right? as a single thread because they're together, right? So it's the same problem you can see. And there's no row buffer there. It's just a bandwidth bottleneck on a link. Okay. Okay, so I think this is a problem in scalable multi-core systems as well. If you look at, this is another work that we may or may not discuss later on. If we don't have time, we will not. But multi-core systems are also growing. And to grow, this is a 64-core system, for example. They may be connected to each other via packet switch routers. And let's say this is your memory controller, or this is something that you're communicating with. It could be a cache bank also. And if you can actually construct denial of service attacks in this sort of system also. This may be attacker cores that basically decide, oh, we want to all access this location. Well, it could be a memory controller. Again, it could be a cache bank. And as a result, other applications that are running over here, it can be denied service. So that's another memory performance hog at the multi-core system level without necessarily accessing memory. And we showed in this work that, again, you can get significant latency increases as you scale the system up if you don't have the quality of service mechanisms in place. Okay, you can read the paper for more detail. There's a lot that goes on over here. And this paper also proposes a simple or relatively simple mechanism to solve the problem as well. So we will hopefully cover interconnects as well. That's also a very critical portion of computing system. I mean, we're starting with memory, but when we talk about memory, you will see that a lot of memory is also interconnect, but basically wires. And the wires are long and energy hungry, and it determines your performance as well as energy. But this is also interconnect bottleneck, as you can see. This is really the access through the interconnect. Okay, and if you're interested, you can read more in this paper. Okay, I think that brings me to the end of this memory performance attacks. Hopefully, I've shown you that breaking the abstraction layers and understanding what goes on in other components and also other hierarchy levels and knowing what's underneath enables you to solve and understand problems, basically. Well, understand and solve, perhaps. Understanding comes before solving, probably. And I think I've given some examples from this memory performance attacks. Any other thoughts? Any other thoughts related to what we've discussed? Any new ideas someone came up with? Okay, yeah, sure, why not? Maybe you have a better solution, right? You don't have to, but if you have it, feel free. For solving the same problem, for example. Or maybe any other examples from real life that you think may be interesting to use in a future lecture. How many other people experience this memory channel partitioning problem at the Zurich airport? Okay, somebody else over there. So you have the same feeling?
Well, but the other part is
Yeah, I know, but it's almost always empty.
it really is, yeah.
Because it's a matter of scheduling, right? When the airport people are there, that may be fine. But if it's always empty, almost always empty, then yeah, that's my point, basically. Basically, I think here's another point. You can get performance isolation, which is the goal over here, isolation for the airport people, or security isolation, whatever you're looking for. Isolation is good for performance and security of whatever is isolated, right? By partitioning. But if you don't need performance isolation, maybe you should not do partitioning. Yes. Can you press the button? Yeah. I think you have to keep holding it.
Okay,
yes.
actually, in my hometown, like there is a subway station, and the way of the elevator may change during the time.
Could you say it again? I couldn't hear still.
The way of the elevator may change in different times.
Oh, okay. Where it goes, right? Based on the quantity of people, let's say, right?
Yes.
Yeah, that makes sense, I think. Yeah, that's more dynamic. I mean, I've seen it also on the roads, right? Sometimes you have roads, let's say you have 3 lanes. Sometimes 2 lanes go this way. Sometimes 2 lanes go this way, depending on how many cars are. Basically, they dynamically allocate the middle lane to which way is a more, let's say, crowded in terms of number of cars. So it's a similar idea, basically, right? Yeah, I like that. Okay, basically, I think I've shown you this picture before also. Memory control is getting more complex. So these issues that we're discussing right now are going to become even more important into the future. I don't think I need to repeat anything over here. Because there are many goals, many constraints, and many metrics, as we will see in the memory controllers, as well as memory interference lectures. Yes?
There's one thing I've been wondering about, because we talk about the memory controller getting more and more complex. And I've seen, for example, some, like in the CPU, the branch prediction algorithm, there's like a trade-off between like how complex you can make it and how costly it is to make it so.
Yeah.
And so I was wondering the same thing, like, what costs are we bound to in the memory controller? Like, can we make it as complex as we want, or is it like too much? Like,
it's always, as we discussed in an earlier lecture, you're always limited by cost, right? No one is immune to that. So certainly it's a similar trade-off. I mean, with branch prediction, there's another trade-off, which is latency. You have to be very quick so that you can supply the pipeline with instructions every cycle, right? Every cycle is 4 gigahertz and increasing today, right? So it's not just cost, but also latency. But cost is also important, sure. But I think you're more limited by latency than cost in branch prediction. In memory controller, latency is important, but it's a bit less important, let's say, because you can actually collect this information off the critical path most of the time. Yeah, but yes, costs, I mean, you need some structures, etc. And again, I think cost is always what value does it provide, right? If it provides something that you cannot get today, like performance isolation, then it's probably cost worth taking. But again, it depends on the system. Make sense? Yeah, we will see more when we go to memory controllers. You will appreciate the complexity more. Branch prediction, while it's an important problem, it's a much simpler problem, right? Yeah. Well, it's also basically you know the right answer basically right away, right? You predict the branch at the beginning of the pipeline. Branch gets executed, and you know whether you've done the right thing or not. That's it. There's no question basically. In memory controller, you don't know whether you've done the right thing. You've scheduled this thread. you prioritize this thread over another thread, or this request over another request, where is the feedback for you to actually get the request that, for you to understand that you've done the right thing? There's no basically, there's no correct or incorrect answer, let's say. You can infer whether you've done the right thing based on some performance metrics that you also need to monitor, but that requires effort also. Yes, go ahead.
You were talking about, well, equal slowdown is a fairness metric, and that sounds, I mean, sounds pretty good to me, but how would you measure the baseline? How would you
that's the
implement
difficult part. We will get to that. You can, if you're interested, you can watch the lectures from last year or past years. But yes, that's the difficult part, basically. How do you measure the baseline, right? You can measure this, you can measure current performance as you're running, easy. But measuring the baseline when you're running alone is a difficult part, because you don't want to stop everyone else. Even if you stop everyone else, what you measure is going to be the measurement that you do at that point in time, not at some other point in time, right? So basically, we have a mechanism to actually estimate that. And we have multiple mechanisms to estimate that, actually. You want to go into more detail? Probably not, because that requires more understanding of the DRAM system.
Yeah, exactly. I'll just watch the lecture.
Yeah. If you're interested, you can. You feel free to go watch the lectures. But that's where that's where really the technical contribution comes, actually, in slowdown estimation. And there are a lot of works on slowdown estimation. We can always do better. I will give you the key result currently. Basically, well, of course, this depends on the application, but on average, you can get an estimation that's between 10 to 15% accurate compared to what you would measure correctly, completely. So we're still 10 to 15% off, let's say. But some benchmarks may actually be much worse off. Yes.
Just make sure I understand, the constraint here is that you have to do this online, right? So you can't stop everything. Like it's a commercial, so you can't just stop everything and one by one sweep them and stuff.
Exactly.
Okay.
You can, but that loses a lot of throughput, right? That becomes a denial of service itself, right? If you slow down everything, or if you deschedule things. Maybe you can press the button so that.
So as part of the factory process, I'm saying, like, well, why can't you just, when the computer is brand new, dedicate like an hour to like characterizing the baseline performances of programs?
Well, that's nice if the application's baseline performance is always the same, but it's input dependent, data set dependent. So yeah, if you're, so people have proposed things like that, and they published papers like that, and I don't like them because of this reason, right? Your program always changes in terms of the input set, right? As a result, your baseline performance always changes. If it doesn't change, then it's an easy problem, right? Then you can do what you say. But then maybe you can optimize in different ways also, or maybe you don't execute your program again. If your inputs are always the same, why are you executing it again, right? That's what I would argue. Yes.
I also wonder whether this can be an interface problem. So the problem may be in the hardware, but ultimately it can also be in the user. So for the security aspect, surely we want to avoid we want to balance the workload. But if for a normal user, maybe he or she just want MATLAB to run faster and don't care about GCC.
Yeah.
So this quality of service, if it can be defined by the higher level.
Yeah.
So maybe this can be an interface problem.
Yeah, exactly. I think there is an interface problem also here. Basically, we need better interfaces so that users can provide what they want from the system, and that doesn't exist as much today. I agree. I mean, you still need the infrastructure that we discussed, I think, underneath, so that you can enforce priorities and enforce the user's wishes. But that interface also needs to be there. Okay, cool. These are very good points. It's good that you guys are, let's say, generating ideas. Okay, I think this is where we will stop the 4A part. And this may be a good time to actually take a break. What do you think? Natural time. So let's take a break until, let's say, 16 minutes again, 2:32. And then we can come back and start with data retention.
Just a question like about the previous lecture, was that primarily or was that completely relating to only memory reads, or does this kind of like, you know, like denial of service also affect memory write requests?
I was going to ask, is the same kind of contention happening at the cache level, or is it only a problem at the RAM level?
Hi, sorry to interrupt. Can you hear us in the room? We can't hear you on Zoom.
Yeah, the microphone is not connected. Can you hear me now?
Yes, now we're starting to hear you. Yeah.
Okay.
Thanks.
So you missed that part of the discussion, I guess.
Yeah.
Tell me earlier. Did you hear anything so far? I'm curious.
Not from you, just the mics in the room were working.
Okay, I see. Okay,
Yeah.
yeah. Okay. So what was the question? Cache level, right? Yeah, basically at the cache level, you have space, right? And one application can destroy the space of another application. Like a very memory intensive application can occupy a lot of the cache blocks, and the other application may not have time to actually fill those cache blocks. And as a result, its cache locality can be destroyed, right? So it's a similar problem, but it's the exact occurrence of it is a little bit different, right? Because it's a space problem, if you think of it that way. It's a space plus an access rate problem, let's say. And we will see that hopefully when we talk about caches. Okay, any other questions? So we talked about caches, we talked about read writes, and there are many other aspects of it. We will see more. Okay, so let's talk about a different problem, but also a very important problem, which is data retention and refresh. And this is, again, very fundamental to memory technologies, especially DRAM. And this is the major scaling issue of DRAM. Okay, I'll just remind you why are we doing these at this point. Okay, so the other example of crossing the abstraction layer is refresh. And let's take a look at that. And we've been talking about DRAM in the system, and just to remind you, it's over here. Now let's start from the bottom up right now. I showed you this picture earlier. You have a DRAM cell, it has a capacitor, it has an access transistor, and it stores data in terms of charge in the capacitor, right? And you have rows of such cells, right? As we discussed, you have many rows in a bank, and then many banks. Basically, you have tens of thousands of rows in a DRAM chip. Now, the problem with capacitor is, or charge-based memory, any charge-based memory is, in this case, DRAM capacitor, is charge leaks over time, right? Through this RC path, the charge leaks slowly over time. And the memory controller, as a result, needs to replenish the charge of each row periodically. And the way it's done today is you need to activate each row every n milliseconds. And typical n today is 64 milliseconds. This is someone determined that it should be 64 milliseconds. We will deconstruct that later on. So there are clearly many downsides of this refresh, right? Basically, whenever you're refreshing, you're consuming energy. And you're doing this just to retain the data. You don't need to read that row. You don't need to read every row every 64 milliseconds. You're just retaining the data so that the charge level doesn't go down some point that you will get bit errors. You lose performance if you were trying to access the DRAM bank or rank. Don't worry about what rank means, but module, let's say, at the same time while it's being refreshed. Because refresh is refreshing a bank, let's say, you've seen the bank earlier. If an access is trying to access that, you cannot do that. The memory controller cannot do that, right? Because the bank is being refreshed. And imagine the bank is being refreshed. Usually, maybe 16 rows in a bank can be refreshed at a time. So you wait for those 16 rows to be activated and closed. So it's similar to what we have seen earlier, except done by refreshes, some necessary operation, basically, for maintenance. This leads to some quality of service and predictability impact because you may have pause times during refresh. Basically, to refresh a bank, it takes time, and a quality of service critical application may get denied service for some time, right? A similar problem again as earlier. And this may also depend on how you handle the refresh. In the past, DRAM used to, let's say the entire module used to be refreshed at a time. As a result, you couldn't access that module for some time. That's not very good, right? The finer granularity your refresh is, the better, because, for example, if you're being refreshed at the bank level, program can access, other programs can access other banks that are not being refreshed. So if you reduce the granularity at which you're refreshing, you can reduce this impact clearly. And the performance impact also clearly. But the energy impact is always there. Energy impact doesn't go away unless you get rid of refreshes. Make sense? Okay. Let's see. Somehow I missed this one. Okay. And I will show you that refresh rate actually limits DRAM capacity scaling. So this is one of the major reasons why you cannot easily reduce the size of a memory cell, because it becomes more leaky. And also it naturally has less charge to store, right? Because it's smaller. As you keep reducing the size of a cell, it becomes smaller as well as more leaky at the same time, which means that refresh becomes a bigger problem. And also at the chip level, you need to, if you want to increase capacity, you want to have many, many more rows. And that also increases the refresh. So basically, as you push for higher capacity, there are three things that really increase the need for refreshing more. Cell become more leaky, cell becomes smaller, meaning holding less charge, and you have more rows in the chip. Make sense? Clearly, more rows mean you need to refresh more in a given time, more rows in a given time. So let's do some analysis. Well, I'm not going to do this analysis. I'm going to leave this as an exercise for you. But imagine a system with 8 exabyte DRAM. And that's exabyte because I keep forgetting what an exabyte is. So it's 2 to the 63 bytes. Does that sound a lot? Yes, but it's not a lot actually. If you look at supercomputers today, you have petabytes and petabytes of memory. I don't remember. I don't actually know exactly how many petabytes in current systems. But we're going to get there, basically. And assume a row size of 8 kilobytes, like what we've discussed before. I guess the easy question is how many rows are there? That's a simple division, right? That's 2 to the 50. Is that peta? Is it? Yeah, I don't remember actually. Does anybody know? Peta, penta, exa? I think it's penta. Yeah. Oh. What is another 2 to the 10, right? So how many refreshes happen in 64 milliseconds? Basically, you need to refresh every row every 64 milliseconds. That's 2 to the 50 refreshes every 64 milliseconds. Now it's sounding a lot, right? 64 milliseconds is not that much time. What is the total power consumption of DRAM refresh? That you need to refer to some data sheets or do some measurements to figure that out. I don't have the number for you, but you can figure this out. It's not that hard. What is the total energy consumption of DRAM refresh during a day? That's power multiplied by time, right? That's easy. Once you get the power number, you just multiply it by the time in a day. It's a good exercise, basically. And you will see that the numbers are actually on the order of kilowatts in terms of power. And this is just for maintenance, right? You just need to maintain the data. It's such a waste if you think about it. And this is becoming worse, basically. I said 64 milliseconds, right? Today, we're already at systems that are refreshing every 32 milliseconds. In some cases, they're refreshing every 16 milliseconds because we have temperature-based refresh, variable refresh in terms of refresh period. And it's going to probably go down. Or you need to do something to reduce it, and that may lead to more energy. So for example, today, DRAM manufacturers are adding error correcting codes to DRAM chips to actually reduce the refresh rates or keep it under control, let's say. But that has its own power consumption, right? If you need to, whenever you read some memory location, you need to correct it first, or you need to check the error correcting codes. That's extra power consumption also. So this problem, even though you may try to solve it, the solutions may actually consume energy themselves and may lead to performance degradation also, or may lead to capacity loss, because if you actually need to store error correcting codes with every row, then you actually are wasting some space, right? That could otherwise be used for data. Okay, so I would encourage you to do this analysis. I don't know if you have it in the homework. Do we have it in the homework, Mohammed? Maybe not this one. Yeah. Anyway, it's an easy homework, let's say. So you can do it. So if you do some projections, and which is what we did in this paper, I'm not going to go into the details of these projections, but this is one projection at the time. It's almost 10 years ago, let's say. And you can see that these were the device capacities at the time. Today we have 16 gigabit devices. I'm not sure if 32 gigabits are out yet, but essentially this is the percentage of time spent refreshing the memory. With 4 gigabit devices, which was the common device of the day, it's about 8%. So this is the percentage of time the device is not available because it's refreshing itself, right? Through the help of the memory controller, of course, because the memory controller controls the refresh today, which is another issue that we may discuss today. So 8%, okay, maybe it's not terrible, right? Still, it's a waste. But as DRAM scales, it becomes much worse, as you can see. So with 16 gigabits, you can see that it's more than 10%. And with 64 gigabits, it's going to be, based on this projection, 46%. Some other projections may put it down to 30%, for example, depending on how you actually do this, right? Still significant. So as device capacity increases because of the reasons we discussed, refresh is becoming a bigger problem, bigger waste, let's say. And this is the percentage of DRAM energy spent refreshing. Of course, this calculation assumes some other things like what is your access rate, activity factor, etc. But with some assumptions, you get 15% of the DRAM energy spent refreshing. And in future devices, you may get half of the DRAM energy spent refreshing. And this number is actually a lot higher if you're not accessing DRAM, right? For example, the DRAM here is being refreshed right now in self-refresh. And almost all of the DRAM energy that's spent is spent on refresh, not access, right? Because I'm not accessing it right now. Unless it's doing some access itself, which hopefully it's not, then it's just spent on refresh. Yes.
So is that curve, would that be flat, I guess, if size was not a constraint? For example, in supercomputers that have like an indefinite amount of DRAM, because like they probably just stack together a whole bunch of like 32 gigabyte chips, right?
Well, not necessarily. Even those supercomputers, remember, applications are also growing. They're not really size constrained completely, because if you keep adding more computers and adding more DRAM, instead of making each chip a higher capacity, then you run into cooling problems, right? Like building level cooling problems. In fact, if you look at those supercomputers, they have huge cooling infrastructures. So I would argue that they also have this problem. I mean, they need to use in order to pack the highest compute and memory density in a given area, they need to use the cutting edge chips. Otherwise, they're making some other trade-off. They have more computers, maybe more chips, more DRAM chips. And as a result, at the system level, they run into other issues. Does that make sense?
I think so, yeah. So the increase in energy consumption from the cooling of stacking together more cheap chips outweighs the increase in energy consumption from refreshing the RAM by increasing the capacity?
So that's a good question. We don't know because this is projection, right? This is not saying we should be doing this. This basically is showing that if we don't do anything about refresh, we will probably get here. Make sense? But yes, I think the trade-off is that I think usually I would say the increase in energy consumption of adding one more computer is higher than the increase in energy consumption when you actually pack more stuff in the same area. Make sense? Yeah, usually. Unless what you have, when you pack your stuff, you're extremely inefficient, right? Yes.
Because you just gave the example with your phone,
yeah.
You need to constantly refresh the memory even when it's not being used, right? Because otherwise the OS and so forth would disappear from the...
Exactly, yeah.
And
there's a self-refresh mode for that purpose.
And can you like selectively turn off certain areas of the memory? Because I guess if it's unused, it would make sense to just only refresh the cells with the OS or the kernel in it and just turn off the rest.
These are good points, basically. And people have proposed similar ideas, yes, potentially. But today, those ideas are not easy to do because, again, because of the problem that I mentioned earlier. Like we take in this course the expanded view of computer architecture, right? We're assuming you should be able to communicate nicely from the operating system to the memory controller, for example. If you don't have that nice communication, which is the case how we design our systems today, then you have no idea which part of memory is actually allocated to something that you should keep refreshing, right? So you should, in fact, existing memory controllers have no idea what part of the memory is allocated and what part is not allocated. So they have to refresh blindly everything in memory. Make sense? But I think your idea is good, basically. You should really be frugal in terms of what you refresh and what you don't refresh, let's say. And with more information, with more semantic, higher level information about what part of your memory is important and allocated to begin with, and important as a second piece of information, then you can do much better. Cool. Yeah, there have been papers that have proposed this, but I don't think it's done yet. You can do it at a module level today, meaning if you don't refresh one module because nothing is allocated there. I think you can do that with some effort, but within a module, it's very difficult to turn off refreshes individually. But our argument is that you should really be doing it at a very fine grain, basically. Maybe even at a row level, right?
But would it be possible with the current architecture to allocate, say, the kernel in one of these modules, or is this still very hard to do?
That's more or less possible. Again, this was based on we had some discussions on bank partitioning, for example. If the operating system somehow figures out the mapping, like topology of memory, and modules are easy to figure out. They're very easy to figure out. Let's say they may even be communicated today. I don't know actually. That should be easy. Yes. Actually, I think if you're interested in this sort of thing, there's a paper that I included in homework 1. It's called RAPID. I think it's software-based methods for quasi non-volatile DRAM. That's trying to achieve this thing basically. At a software level, it's trying to get rid of refreshes as much as possible. Not exactly the way you described it, but take a look. Yeah, that's a good paper to review also, I would suggest. Okay, so that's energy. Clearly, we don't want a future, let's say, where you have a DRAM chip and half of the time, almost half of the time, you cannot access it because it's doing refresh, and almost half of the energy is spent refreshing, right? That's not good. That's not what we want in general. Okay, so the question is, how do we solve the problem? So let's talk about it first. I think the observation is that all DRAM rows are refreshed every 64 milliseconds. Maybe you can attack this part, right? I think you attacked it a little bit, or maybe you can attack it more. Like, why is this true? Does this have to be true, right? You said that you don't want to refresh anything non-critical, let's say. And maybe you write the other stuff into the solid state drive, right? Of course, there are trade-offs associated with it also, but sure. Okay, any thoughts? No thoughts? Yeah.
I'm not sure. Like, I think I'm not sure if why it's 64 milliseconds. I don't
That's a
know
good
why.
question. Yeah, that's a good thing to ask, right? Why is it 64 milliseconds? Maybe you have an answer?
Well, not really, but I do have a thought.
Okay.
Guessing it has to do with the transistor technology. So if we wanted to refresh less often, we would need transistors that leak less, or
Often.
maybe a different material for the capacitors. I don't know, just
Maybe, yeah. Yeah, basically make the technology, let's say, better so that it doesn't leak as much. That's very difficult, it turns out. Yeah. Yeah, leak from the capacitor and the transistor path. Yeah, absolutely, it does. And I think he's trying to fix that. Yeah, but usually those solutions are very difficult in DRAM today because you reduce the circuit so much. You need to change the material either. But then that's also difficult because, yeah, it's difficult basically. New materials are costly in general. Yes.
So if I remember correctly, I think it also depends on the production process, and there's some variety between the different rows, and you can exploit that by measuring. And I think this was a paper that was discussed in the seminar course last year.
Oh, okay, you took the seminar course, so you have an advantage. That's good. That's fine. Yes, exactly. That's what I'm getting at also, basically. So basically, this goes to the heart of the question also. Why 64 milliseconds, right? Who determines 64 milliseconds? And this is a convention, basically. DRAM manufacturers say that I guarantee you that my chip is going to have no cells that are going to fail if you refresh it if you refresh every cell every 64 milliseconds, right? You can think of it as a convention, right? How is it decided? Well, it's decided so that the DRAM manufacturers can, let's say, maximize the yield of their chips, right? Because most cells, let's say, don't fail. Well, you need to guarantee that your chips don't fail. First of all, we don't know if that's true, if they're guaranteeing that. I actually have doubts that this is being guaranteed completely today because it's a difficult problem. But let's assume that it's being guaranteed. But this means that there's no cell that's going to fail if it's refreshed every 64 milliseconds. But this doesn't tell us anything about when a cell is going to fail, right? Maybe there are some cells that are going to not fail, even if you don't refresh it hundreds of seconds, right? And that is the case, actually. Basically, there's a huge variation in terms of the, let's say, retention capability, data retention capability of the cells, because there's a huge variation in the manufacturing process. Whenever you manufacture a chip, not all cells are equal, right? Some have small capacitors, some have bigger capacitors, some have leaky transistors, some have not leaky transistors. So there's a lot of variation, actually. As a result, there's a huge variation in terms of the data retention capability, time, as we will see. So basically, critical thinking says, do we need to refresh all rows every 64 milliseconds? Well, I guess I don't have the answer right now yet, but what if you knew what happened underneath in DRAM cells and exposed that information to upper layers? So this is what I'm getting at. Basically, if you magically construct the retention time profile of all DRAM cells, this is all your DRAM cells, set of DRAM cells, it looks like this. Basically, the little portion, the red portion over here, are the fraction of cells or the cells that can retain data somewhere between 64 to 128 milliseconds. Very little. This slightly bigger, but still little portion is the cells that can retain data between 128 to 256 milliseconds. And the vast majority of cells can retain data for a time greater than 256 milliseconds. This is based on measurements, basically. You can, of course, make this more finer grained, right? You can make it 1 microsecond, then see. You can make it 1 second, then see what fraction is like that. I will show you the curve. The curve looks like this, basically, in a little bit. But if you know this, and if you know how much a cell, for how long a cell can retain data, this is called the data retention time of a cell, then you can identify this, and you can basically refresh everything according to how long it needs to be refreshed, right? How often it needs to be refreshed. And based on this picture, you can immediately say, if I do that, ballpark, well, I will get rid of 75% of the refreshes, right? Because most of DRAM, I should refresh every 256 milliseconds. Make sense? Yes.
Could we use somewhat of a hybrid memory technology to for the most current data to being stored in cells that are refreshed every 256 milliseconds, and the data that needs to be that is really important in DRAMs that are refreshed every 64 milliseconds to reduce the energy consumption?
So, okay, I didn't quite understand. You basically want to put critical data here and non-critical data here? But if you have this, and if you're already exploiting this, why do you even want to deal with figuring out what's critical and what's non-critical? Meaning, basically, if you know this profile, and if you're refreshing based on what I show you, you will be reducing energy consumption anyways, right? That's right. You need to know that. Yes, yes. You need to know the cell level property, not the property of the data that's stored in it, right? Okay, makes sense. Maybe you can do some other optimization based on your critical data. Maybe you can say, okay, this exploits a different thing. But I think what you're getting at is, if you have some critical data who's reliable to you care about, refresh it often. If you don't have some critical, if the data is not critical and you have error tolerant data, don't refresh it as much, right? And live with the penalties of it, meaning getting some bit errors once in a while. Certainly that could also work, but that's exploiting the property of the data and not the property of the cells. Yeah. And that has been proposed also, by the way. But you need to be able to control your bit error rate somehow, right? You cannot basically turn off refresh, because turning off refresh actually leads to a lot of bit errors later on. But maybe, yeah, it depends on the bit error rates. I didn't show you bit error rates, right? If you don't refresh a cell for, let's say, 1 microsecond, how many bit errors do you get overall, right? Okay, this makes sense so far? Okay, so this is purely based on manufacturing variation, and manufacturing variation is everywhere. That's something that we cannot avoid. It's in nature, right? Everything has variation. I mean, even genetics has variation, right? So it's everywhere, and people are not also figured out how to perfectly manufacture things. So you will always have manufacturing variation in anything that's manufactured. Okay, so why do we have such a profile? Basically, that's the answer. Manufacturing is not perfect. Not all DRAM cells are exactly the same. Some cells are more leaky than others for various reasons. Again, they may have poor capacitors, poor transistors, and poor interconnect also. And this is called manufacturing process variation, basically. So how do you take advantage of the profile is the next question, right? I gave you one idea, but there may be multiple ways of taking advantage of this profile. Assume you know the retention time of each row exactly. Now, this is an assumption. We will see how difficult it is to actually get this information, which is the exciting part, really figuring out how to get this retention time. But let's assume that we know it perfectly. What can we do with this information? Who do we expose this information to? How much information do we expose? Clearly, this affects the complexity that you have, right? Because this may be a lot of information, right? For every single row, I'm not talking about the cell level, because even though I showed you a picture at the cell level, you refresh at the row level, right? In DRAM. For every single row, you need to store this information, right? That could be expensive. Okay, that could affect overheads, power consumption, verification complexity cost. And then I think this is getting back to how do we determine this profile of information exactly? And who determines it? That's also another question. Is it the DRAM manufacturer? Is it the system designer? Is it the person who wants to reduce refresh? Basically, DRAM manufacturer does nothing for you. System manufacturer does nothing for you. You as a user say, okay, I'm tired of this refresh. Let me reduce it. Okay, that's why I think this is a very interesting topic, and it also spans across the stack. And even people may propose, for example, I don't know, program level changes that allocate potentially long-lived data structures to things that can keep data for longer, right? To rows that can keep data for longer, whereas your short-lived data structures can go to rows that that cannot keep data longer. And as a result, you may actually get rid of the refreshes in hardware if you can do that. But of course, that's not easy to do. But there have been proposals like that also. Okay, any thoughts? Any ideas? I'm going to give you some ideas, but maybe you have some ideas that you want to share. Yes, please. Yeah, please.
If it's
so
even
other people can hear.
Yeah, I was wondering if it's like statistically feasible to classify a whole stick of RAM, to put a stick of RAM into like a category A, B, or C, where category C are the worst ones that have to be refreshed every 4 seconds, whereas like the stick A can you know, it's completely free of bad rows and just only needs to be refreshed like every 256 milliseconds.
I see. When you say a stick of RAM, it's a DRAM module, right? Yeah. Yeah, I mean, it'd be nice to be able to do that, but in our experience across many chips, and based on the understanding of process manufacturing variation, there are always some cells that are really weak in any, let's say, stick of RAM in any module. So it's very hard to do this at the module level, basically. You have to really classify cells within a module, within a chip, in fact. Yes.
But then couldn't you just deactivate the rows, like get rid of the rows with the bad cells?
Yeah. So that's one solution, basically, right? If you have this retention time profile information exactly, then you can basically say, don't allocate anything to those rows, right? And that's, I think, a good approach, potentially. The problem is now the operating system needs to know this somehow. Somehow you need to get rid of these from the physical allocation space, let's say, in the DRAM. Yes.
Does the operating system really need to know this, or can the controller of the DRAM cells do this?
Potentially, yeah. It could actually have another mapping layer, right, internally. Yes, I think it's possible. Yes, you're thinking well, I think, in that direction. So if you usually controller also has another mapping layer. You basically extend that mapping layer to map out these bad things, but you need to map them somewhere else, right? Where do you map them?
I think, could it be done a bit like on the SSD?
Yeah, but that's sure. It could be done anywhere. The problem is the problem is this, right? Operating system assumes you have some amount of DRAM, some number of rows, let's say, whereas in reality, the memory controller is managing a smaller number of rows, and the operating system, like the access comes, and it's in a physical address that, from the perspective of the memory controller, should not be mapped to. Where do you store it? If it stores in SSD, now you have a huge system level problem, because you're the memory controller and you have that request. You're asked to service it. How do you even go to the SSD now? Right? So in current systems, you don't have that flexibility. Ideally, yes, ideally, I agree with you. It should be fungible, right? Meaning you get a request, and that request should be routed to any place where data could be stored. And we will see that actually in lecture 11, 13 or something, where we talk about these emerging memory technologies and heterogeneous memory. Ideally, you should have a unified view of data, and the accesses can be serviced by, let's say, a meta controller, and the meta controller directs other controllers to service the access. But we don't have that today. That's very hard to do this without support from the operating system, without information going to the operating system today, right? You need, at the operating system level, you need to map out these physical addresses basically somehow. But I like the direction you're thinking. Yeah, unfortunately, systems are not that easy to change. Yes.
Is there any non-volatile memory devices that can replace DRAM in the future?
Yeah, we're going to talk more about that. Basically, you're trying to get rid of this problem, right? You find that it's a hard problem. Yes, get rid of it. I like that idea also. Potentially, but there's nothing that comes very close yet, right? But we will discuss that. Yeah, if an unvolatile resistor memory replaces DRAM, then you may get rid of the refresh problem. You may have other problems except other than refresh, of course, endurance, for example, like we discussed yesterday. That's a trade-off. Which one do you like better, refresh or endurance problems? Yes.
I just wondering why the manufacturer don't just disable those cells with the short lifetime.
So that's another thing that you can. That's another solution basically. You're basically saying manufacturer figure this out and disable those things, right? Yeah, I mean that's a possibility. Yes.
I just wanted to ask, because we discussed building them at the operating system level, would you do that at the level of virtual memory or some other level? And if we do it at virtual memory level, I guess there still could be cells that we have to use, right? That we can't even disable.
Well, you do it from the virtual to physical mapping level, right? Basically, in virtual memory, you have virtual pages and you need to map them to physical pages. Some part of physical space is not available anymore. Make sense?
Yeah, it does, but I guess okay, makes
yeah. Yeah. Going back to your point about manufacturer disabling this, a similar problem exists, right? Manufacturers give you 16 gigabyte memory. And again, that gets exposed to the operating system. If manufacturer magically disables these, they have to replace them with something, right? If you want to have this contiguous view of memory again at the operating system level. Yes.
I don't remember. Why can't the rows be refreshed at like their rate, their corresponding rate?
Because you, why can't they be refreshed at their rate? Because that's not how it's done today.
Why? Like, what's the limit? What's the limiting factor?
Well, we will talk about that. Basically, that's going to be our solution. Yeah, that's going to be the solution that I will describe. But it requires implementation and also some. Basically, you need to store which rows need to be refreshed at what rate, right? Somewhere. So that's I think that's a more feasible solution, I would say, than everything we've discussed, because that keeps the solution at the memory controller level, let's say. At least in the short term, more feasible solution. But we will discuss that. Yes.
I was thinking, isn't it something that DRAM modules already do today, like to have enough sets, like to have an even more physical address than the physical address?
Yes, that's true. That's true. But they're used for other purposes. There are other faults than refresh. For example, manufacturers, they manufacture DRAM. They find out that some rows don't work. They're hard errors, meaning you cannot write a value to a row, a cell in a row. What do? They map out that row and remap it to some other row internally. You can do that also for these rows, yes, but these are a lot of rows. I will argue that there are not a lot of rows also, so you could argue the other way as well. Yes.
I'm wondering how the refreshing works, because it must know which cells to refresh and which not. Because if like there is a bit 0 in the cell, for example, so if the power is low, you don't have to refresh it. So how does it manage to do it?
Oh, I see. So refreshing is actually, you can think of it as reading the data and writing it back. Yeah, that's how it's currently done. Make sense? At the abstraction level, basically. Activate pre-charge. Yes.
So now I think the entire discussion is about the left column, right?
Yeah.
But even if we fix this problem, I mean, we get a 4x improvement, I guess.
Yeah, exactly.
Which improves, like it's gonna shove the problem a few years into the future, but it doesn't solve DRAM, right?
Yeah, yeah. But 4x is not bad. It's better than 0%. But yes, I agree. And we will see that in the results also. I will say that this is, well, whatever the solution that I'm going to describe is a good solution, but it's not good enough for energy scaling, basically, into the future. So there needs to be more solutions. But that's a very good point, basically. Don't be satisfied. Okay. Nothing else? It's a good discussion. Okay. So basically, let's go into what we did, basically. So you can determine using experimental infrastructures like what you suggested, for example, with an FPGA board, FPGA-based memory controller, the retention time of these cells. And that's what we did basically in at least 2 works, but there are other works also I will discuss. This is another work where you have many FPGAs. And basically, we actually developed this platform initially for understanding this refresh problem. It's a DDR3 DRAM testing platform using some FPGA board. It's temperature controlled. We developed it in 2011 or so. And we initially tested 248 DRAM chips from 5 manufacturers. And these are the capacities, as you can see. So basically, we verified this. You see, this is real, basically. You can verify it with real measurements. And this is an example graph. This is actually data from Samsung before we verified it. They actually showed something like this as well, but we replotted it so that it makes sense, let's say. Basically, overwhelming majority of the DRAM rows can be refreshed much less often without losing data. So if you actually put some numbers, this is a refresh interval on the x-axis and the cell failure probability on the y-axis. Clearly, we don't have any failures below at 64 milliseconds, let's say. But as you increase the refresh interval, you start getting failures. So in a 32 gigabyte DRAM, you get about 30 cells. And these are randomly distributed across the chip because of random process variation. So you get 30 rows, let's say. Not bad, right? At 256 milliseconds, you get 1,000 rows. But you keep climbing up the curve and it increases exponentially, right? As you can see. So maybe maybe you can map these out, as you said, and bear the consequences. But we're going to refresh them at different rates. So basically, the question is, can we exploit this to reduce refresh operations at low cost? That's going to be the key. And we wanted implementability, so operating system mapping out was not something we wanted to consider at that time. So I think I rephrased this. Basically, the key idea is very simple. Refresh weak rows more frequently, all other rows less frequently. And that's this paper. That's the first paper we did on DRAM, in fact, I would say. Well, one of the first papers. And the mechanism is very simple. I'm going to explain the mechanism. First of all, you need to profile, identify the retention time of all DRAM rows. This can be done at design time or during operation. And there's a huge design space over here, which later works examined, as I will discuss. After that, you need to store this information somewhere. How often do you need to refresh every row, right? And this becomes costly potentially, right? Depending on the size of your DRAM. If you have millions of rows, this is storage of millions of bits, right? Where do you store it? So, and the memory controller needs to have fast access to this, right? If you want to decide whether or not to refresh a row based on this information. So we store rows into bins, we bin the rows, and we use Bloom filters for efficient and scalable storage. How many of you know about Bloom filters? Okay, a small fraction. So that's good. Hopefully you're going to learn something interesting today. In fact, this is one of the papers that I also assigned as a paper to review. And it's one of the easy ones, let's say, because it's very short. This was written in 1970. Okay, so basically, we bin the rows into 3 bins, but paper discusses the general approach, of course. You can have as many bins as you would like. Of course, there's a trade-off between refresh reduction and storage cost. And it turns out for these 3 bins, you need very small storage because we use Bloom filters. Okay, and then refreshing is easy after you know this information, right? Memory controller refreshes rows in different bins at different rates. It checks the bins to determine the refresh rate of a row, basically. So you can implement it in multiple ways, but there's very little change to the memory controller. Okay, so let's take a look at the takeaways first before we go into how we do it, right? So assuming that you've implemented this nicely and you put this in a simulator and you simulate it, what the benefits you get are, this is what you get. Well, I already discussed this. Refresh reduction is about 75% as expected, right? Based on the picture that I showed you. An overwhelming majority of DRAM cells can retain data, have to be refreshed every 256 milliseconds. As a result, you can reduce the refreshes by almost 4x. It's not exactly 75% because there are some cells that need to be refreshed still more often. And also, Bloom filters are not perfect, as we will see. And this leads to a dynamic energy reduction of 16% in DRAM and an idle DRAM power reduction of 20%. You can read the paper for what those means. And it also leads to a performance improvement, 9%. That sounds good, right? So this is one of those ideas that improves performance and energy at the same time. It's getting rid of refreshes. And you can see the energy per access over here with different device capacities. This is the beauty of simulation, right? In simulation, you can study a wide design space. So device capacity, and this is energy per access. You can see that we can reduce energy per access by 16%. That's what this is over here. But that reduction is higher as you go to higher technology nodes, meaning higher densities. But you also see that energy per access, ideally you should keep energy per access constant across scaling generations, right? Or lower it if possible, right? If your technology scaling is friendly, your energy per access should go down as you scale the technology. But today we're at a point in DRAM that your energy per access is increasing, as you can see, significantly. And we want to keep it constant. We actually reduce it significantly, but it's still not constant. It's still growing as the chip grows. Yes?
I'm not sure I understand the metric energy per access. Refreshes or
yeah,
something?
Yeah, you can think of it as energy per refresh, yes.
But so is it by, so it's not per access from software, for example?
No, not software. This is DRAM access. Yeah, this is DRAM access. You can think of refresh as DRAM access, right? It's actually the same thing because you're activating and pre-charging, which is the same thing you would do when you read a row. We're just not doing the reads. Yes.
But still, sorry. The continuation question is then, if a refresh is considered an access and you're reducing the number of refreshes, how did you reduce the energy per access?
Well, I think there are multiple ways of answering that question, right? First of all, you can look at all of the energy that you spend in DRAM and divide it by the whole number of DRAM accesses, and you will still reduce it because you're reducing the DRAM energy, right? If you're considering all accesses. Make sense? Okay.
So just tying in the previous lecture, assuming there's a 100% memory bandwidth utilization, does this mean that you're also improving your system performance by 75%?
Well, I guess it depends on what you mean by performance, right? If your memory bandwidth bottlenecked, yes, maybe, right? And depends on the application, right? If you have interference between applications, it may not be 75% overall. But if it's one single application that's bottlenecked by bandwidth, maybe that's correct, yes. Yeah, so you can see that the performance improvement is also nice. This is, again, multi-programmed application, so there's interference between applications also. So it's a complex equation. Well, there's no equation, you have to simulate it. But basically, you get 9% performance improvement with when the refresh is less of a problem, and you get a lot more performance improvement when refresh is more of a problem, basically. Because you're really alleviating the memory bandwidth bottleneck, as you see. That's why the performance improvement is huge. Make sense? Okay, so this sounds like a good idea, right? Now let's take a look at it a little bit more deeper. And this is another potential reading for your homework, one assignment. And if you're interested, there are further readings also that are related to refresh. Well, I guess we're not going to take a deeper look right now, but I'm going to take a deeper look if you're interested, since we have time. This was a potential natural break if we didn't have time. So basically, I think I didn't tell you exactly how it's implemented, which we're going to do now. But if you actually do it, then basically what we've done is we've broken the abstraction layers between the architecture and the circuits, let's say, memory controller design and the device level. Now we have an understanding of how the device is, and we're exposing to the memory controller, and the memory controller is taking advantage of it to actually get rid of an important problem. Well, get rid of is maybe too strong, but that's how it is. And clearly, cooperation between multiple components and layers can enable more effective solutions and systems. Okay, do you guys want to dig deeper? Okay, I see a lot of head nods. Or do you want to stay at this abstract level? That's another possibility, right? So digging deeper will give you more information of how difficult this is, and also how you can actually make it work. So I think you have to dig deeper, basically. How do you make this radar idea work, right? And in general, I think coming up with ideas is good, and it's always good to come up with more ideas. But in general, you can come up with ideas. If you're thinking correctly, if you're thinking well, if you're focusing on the right problems, it's easy to come up with good ideas, let's say. And good ideas, this is a saying in American English, good ideas are a dime a dozen. I don't know who it's attributed to, but it's anonymous, I think. But the difficult part is making them work in general. So if you have a good idea like radar, for example, how do you make it work? Okay, let's take a look at the mechanism first. Basically, we want to profile, we want to bin, and we want to refresh based on the binning information. So there are three dependent steps, right? Binning is dependent on the profile information, and refreshing is dependent on the binning information, right? So profiling, the radar paper initially hand waves this. And sometimes you need to do that in research. We knew that this was a difficult problem, but we had to hand wave it so that we could actually show the benefits of doing this, right? Basically, the radar paper proposed a very simple profiling mechanism that is not going to work in general. And that basically says, write the data into the row, prevent it from being refreshed, measure the time before data corruption. That sounds good, right? Intuitively, it makes sense. Now, if you go into the details of it, you need to actually make this a lot more comprehensive. You need to make this robust. First of all, this works if the retention time of a row is consistent every time you measure it, right? Every time you measure it, you should get retention time T, which is the natural retention time of the row. But it turns out that's not the case. Retention time of rows change based on temperature, which radar paper addresses actually. That's fine. At high temperatures, you need to refresh rows more often because things become more leaky. But there's something that the radar paper doesn't address, which is called the variable retention time phenomenon. And if you remember Samsung and Intel's paper that I mentioned yesterday, they say that this is a big problem. And this is the idea of randomly, a row changes its retention time at random points in time. And we will see why that happens, and we will see how you can potentially solve the problem. So later papers solved the problem, but we had to assume something because we had no idea how to solve this problem at the time. Does that make sense? Sometimes you have to take a leap in research, basically say, okay, I don't know how to solve this problem, but I have this idea. If that problem is solved, then this idea is going to be very effective. And let others solve that problem. In this case, others were us, and also others worked on it as well, but we solved the problem later, basically. So I think it's important to do this, and it's important if that the research community is receptive to this sort of leaps sometimes, because if you don't take that leap, then you don't show the benefits of an idea, right? You cannot solve all the problems in a single work, especially if the problems are difficult. Okay, so hopefully this is clear, right? This makes sense. Basically, you keep measuring at different intervals to figure out whether you have errors, and at the time you get errors, you say that, okay, I cannot retain data for that interval. So I have to refresh with the previous interval's length. Okay, assume that that works. Well, I guess the question is this really easy? Basically, not really. Well, I guess I will go into more details of how it is, but I'm going to, yeah, okay, let's go into details of how it is. Can anybody guess why it's not easy? Well, I've already given you one example, actually, variable retention time, but there's another reason why it's not easy. Yes? That's right, yeah, time is also a problem, yes. But I mean, it's an important problem. You could do it. You could dedicate some time. But if you're doing it online, yes, that's a big problem. And you may need to do it online based on the variable retention time phenomenon. Okay, yes. Yeah, basically what you need to do is you write data to the row, prevent it from being refreshed, and you read the row and compare to what you've written, yes. Now that brings us to one of the problems. What do you write to the row? Is all zeros, all ones, random data, some pattern? And that's the other problem, is second problem. Retention time of a row is dependent on the data pattern. Yes?
Would the reading of the row potentially affect how quickly it loses charge as well?
No, not normally. Basically, reading is the same as refresh. Whenever you're reading the row, you're refreshing the row. If it has lost charge by that time, it's lost charge. If it's lost charge while you're reading, well, too bad. It's the same thing, basically. Your refresh is too late. Does that make sense? Because you're reading it only once to determine whether it's lost charge. You're not doing intermediate reads. If you do intermediate reads, you're refreshing the row anyways. Okay, so I mentioned basically the two problems. The retention time of a row is dependent on the data pattern that you store in the row, as well as the rows around it. So now you have a huge search space. What is the worst case data pattern? Does the worst case data pattern depend on the row? Does the worst case data pattern depend on the temperature? Does the worst case data pattern depend on the chip? So there are many questions here. And the second question is even harder. Variable retention time phenomenon. The retention time of a row depends on time in a random manner. It changes randomly over time, basically. Then how do you even get the retention time of a row? Then, of course, the question becomes, how much does it change? What is the time scale at which it changes? So there are a lot of questions that you can ask to at least understand the problem, right? Okay, let's start with the data pattern dependence. I think I already said this. Retention time of a DRAM cell depends on its value and the values of the cells nearby it. Of course, let's dig deeper. Why is this the case? Well, because when a row is activated, when you activate a row, all of the bit lines in the row get perturbed simultaneously, right? This is the row. Row is called a word line also, if you remember. And you activate a row, all of the bit lines get perturbed simultaneously, as you can see. Yeah, I already said these basically. And there's electrical noise on the bit line, basically. There's electrical noise on this bit line. There's electrical noise on this bit line, on this bit line. And this electrical noise affects the sensing of each DRAM cell in the row. And the magnitude of this noise is affected by the values of nearby cells due to coupling, basically. So you have bit line to bit line coupling. So if you're looking at the cell, you have coupling between these two bit lines that affect the sensing of the cell. And how much effect you have depends on whether you're reading a 1 or 0, and whether the values of these cells are 1 or 0, because that determines the voltage differential between the different cells. Yeah, that's what this is trying to show, kind of. And there's bit line to word line coupling also. There's electrical coupling between each of these bit lines and the activated word line. And the amount of that also depends on what's the data values that are stored. What is the charge that's stored in the capacitor? Again, because of voltage differentials that you have. I don't want to go into a lot of detail over here, but there are papers that describe this voltage differentials a lot more. Essentially, the key takeaway is retention time of a cell depends on data patterns stored in nearby cells, as well as the cell itself. And if you really want to find the worst case, if you really want to find the worst case data retention time, you need to find the worst data pattern that leads to that retention time. And this is not easy, basically. But I mean, you could argue that there could be some solutions to it, right? Basically, any retention time profiling mechanism must handle this data pattern dependence. And intuitive approach is identify the data pattern that induces the worst case retention time for a particular cell or device. But that's a big search space now. So the first problem is, and there are multiple problems that affect this. It's very hard to know at the memory controller which bits actually interfere with each other, because you don't know which bits are actually mapped next to each other. Memory controller doesn't have a good idea of the geometry or topology of DRAM also, physical DRAM geometry. Logically consecutive bits may not be physically consecutive. And our later papers actually show this very clearly. I'd recommend looking at our DSN 2016 paper, for example, that looks at data pattern dependent failures in DRAM. And there's also remapping, as we discussed earlier, for remapping reasons internally, right? There's for hard faults, you remap faulty rows to rows that you know work well, and faulty columns to columns that you know work well. So there's this remapping. As a result of this remapping, what appears to the memory controller as adjacent may not be physically adjacent in DRAM, right? Because memory controller has an address space that's now logical, which is different from the really physical address space inside the DRAM, right? That's the idea. So you have a decoupling between the view of addresses you have at the memory controller and the view of addresses you have that are based on adjacency, physical adjacency inside the DRAM chip. So that's why this is very hard to do, actually. So you need some support from the manufacturer, or you keep doing exhaustive testing and figuring out, convincing yourself potentially that this is the worst case data retention time. And we did a lot of studies actually to figure out the worst case data retention time. Not the data time, worst case data pattern that leads to the worst case data retention time. It's not easy, basically. You need to test a lot. Okay. And also there are second order bitline coupling effects that are even harder to determine. Basically, what I showed you earlier, okay, maybe you're affected by adjacent cells, but maybe you're also affected by cells a little bit farther at a second order. And that's true, actually. We see that as well. So that complicates the profiling as well. That said, I think with good reverse engineering, you can do a lot of this. Basically, again, you can take the security perspective, right? You can say, okay, I can reverse engineer anything. And that is almost true in DRAM also, except for the words that are remapped. They cause a lot of problems. But everything else you can reverse engineer mostly. And you can build an understanding of the remapped rows also if you do enough testing, basically. So I think data pattern dependence is still not as hard as before, but you need to be careful, basically, whenever you're doing retention time profiling. Does that make sense? Okay. Okay, let's look at the second challenge, which is even harder. This is called the variable retention time phenomenon. And the retention time of a DRAM cell changes randomly over time. And as a cell alternates between multiple retention time states. And this is actually a very interesting phenomenon. This was known since 1987 from a seminal paper by Yaney in IEDM. It was also demonstrated in 1992 in another very interesting seminal paper in IEDM. Basically, these folks show that leakage current of a cell sporadically, randomly, changes when charge gets trapped in the gate oxide of this DRAM cell access transistor. So, and this is a random process, basically. Randomly, charge gets trapped, and you become more leaky. Basically, the way you become more leaky is when the trap becomes occupied, charge leaks more readily from the transistor's drain. And you can read those papers that I mentioned. They're actually very interesting. And that leads to a short retention time, clearly, if you're more leaky, right? This is called TAGIDL. Well, you can read the trap-assisted gate-induced drain leakage. And this process appears to be a random process according to earlier works. And our paper also showed that it is a random process. Basically, we provided more data. So basically, the second challenge can be summarized as follows. Worst case retention time of a cell depends on a random process. It's a random number, basically, let's say. It's not as bad, of course, because it's not true for all cells. It's especially true for those cells where you're at the boundary, right? You need to be very careful for those cells. You don't want to misclassify cells. If your variable retention time phenomenon happens at between, let's say, 10-second retention time interval and 9-second retention time interval, maybe you don't care. Those are cells that are strong. You need to be very careful at the boundary conditions so that you don't misclassify. So you can focus on those really dangerous cells, let's say. Okay, but still, it's not an easy problem. You need to find the worst case despite this. So this is an example of a VRT cell. This is done at the room temperature. That's why the retention times are so high, as you can see. But you can clearly see that there are multiple states that the cell goes through. Most of the time, it can retain data that many seconds. But some of the time, tested over hours, it drips down to a very low retention times. Okay, this is another example of how common this is. Basically, this is minimum retention time of the cell on the x-axis, and this is the maximum retention time observed for the same cell on the y-axis. And this is a density plot of the cells. How many cells are at the xy point, right? And the darker the point is, there are more cells that are at that xy point. And if there is no variable retention time, you would not expect this curve. What would you expect? You would have an x equal y line, right? Everything would be lined up along that. Maximum and minimum retention time should be exactly the same, right? For every single cell. But that's not the case, as you can see. You can see that most of the cells are actually over here, meaning, so, okay, I should also say that we did not test the retention time higher than 6.1, I think, seconds over here. So that's why we have an upper limit over there, because you have to stop testing at some point, right? So you can keep going hundreds of seconds, and there's no end to this. And we decided 6.1 seconds was it to prove our point. And that proves our point, basically. Clearly, a lot of cells, most failing cells exhibit VRT. Of course, this is from the population of failing cells. If a cell doesn't fail, then they don't have VRT, right? Well, they don't seem to have VRT in the testing conditions, of course. And many failing cells jump from very high retention time to very low retention time, as you can see. So minimum retention time is 1, and maximum retention time is 6.1, which is the maximum tested. And this is true for many chip families, as you can see in the paper. And I think these are very interesting results. This is what you can do with an infrastructure like what I showed you earlier, like FPGA-based infrastructure. It's very hard to do these studies in a real system. Refresh is easier to do on a real system, but it's still hard to do on a real system. Easier, I should say, easier than some other things that you can do to DRAM, like reducing latencies, etc., or voltage. Okay, so what are the implications of this random process on profiling mechanisms? First of all, what are the problems? There doesn't seem to be a way of determining if a cell exhibits variable retention time without actually observing the cell to exhibit the variable retention time, right? And it's a memoryless random process. And second, variable retention time actually complicates retention time profiling by DRAM manufacturers. There's something that is not shown in the previous result. So if you actually expose a DRAM chip to very high temperatures, you can induce variable retention times in cells that were not previously susceptible to variable retention time. Basically, you can change the variable retention time profile of cells. Let me put it that way. If you expose a chip to high temperatures. So you should ask the question, when do I expose a chip to high temperatures? Well, whenever you're soldering a chip to a module, let's say. That's one case. So this could happen during soldering of DRAM chips. And this is clearly outside the manufacturer's control, right? Manufacturer manufactures a chip, somebody else puts them on a module or in a board. And if they expose the chip to very high temperatures during that soldering process, who knows? So basically, manufacturer's retention time may not be accurate, even if they find these variable retention time cells. Right? So you could say, basically, I think this is here to show that you could say, manufacturer, provide me the retention time profile, and whatever they provide you may not be good enough for it. In fact, may be wrong. Okay, so that's why this is a system level problem also. So of course, this paper also suggests how you should do it. I think this is a good idea, basically. This was a suggested idea in 2013. Basically, use error correcting codes. Continuously profile DRAM online, meaning once in a while, test the retention time of rows. Reduce the refresh rate. If you get errors, you reduce it too much, right? And hopefully you have error correcting codes that correct the errors. So you have a feedback mechanism to decide whether you reduce the refresh rate for a given row too much or not. If you keep doing that nicely, you can perhaps filter out these variable retention time cells. Because these variable retention time cells are interesting because sometimes they're in a low retention state, sometimes they're in a high retention state, and they keep jumping up and down. And ECC can catch when you're doing something wrong. But of course, the ECC needs to be strong enough to actually catch all of the bit errors that you get. Yes?
What temperature range in degrees are we talking about when you say very high temperatures?
Yeah, so that's a good question. I mean, there's not enough data in the field about it, but it could be as high as 100 degrees, 120 degrees.
But because I was thinking, so if your computer runs hot from computation, could that induce VRT, or would it have to be way hotter?
So it can. Basically, at higher temperatures, you see this VRT phenomenon worse, basically. So that's why, I mean, in general, refresh becomes worse, or retention times become worse with higher temperatures. But usually the soldering temperatures are much higher than what is the specified operation temperature of a computer. But it's the same phenomenon, basically. Okay, so basically, if you want to do this, you need to keep the ECC overhead in check. Any questions? I think these are fascinating phenomena. Yeah, go ahead.
I was just curious, how does the endurance of a DRAM module impact the...
Well, when you say endurance, what do you mean?
Like, does an older module, like a module we've been using
okay,
actively for years, is it like more susceptible to VRT or?
Yeah. So that's a good question also, and we don't know exactly. There's not enough data in the field in terms of DRAM aging and the effects of aging on errors, basically. Maybe you can collect some. You can do research on it. It's not easy research to do, also. Yeah.
Would there be a way to like wear out, like purposefully wear out DRAM module just by like?
I mean, that I know that is very difficult, basically. At least in the current DRAM technology, it's very difficult to wear out the DRAM. Let's say even a cell by keeping on writing and reading. It doesn't have those wear out mechanisms that flash memory has, for example, or phase change memory has. But this doesn't mean that retention time doesn't get affected. Let's say you have a brand new chip versus a chip that's in use for 10 years. That chip may have worse retention times, right? I don't know. It's still working. It's still within the specification, but maybe the retention time has gotten worse, right? I don't know. That needs to be tested, right? And that's a difficult test to do, as you can appreciate, probably. Yes, you had some question.
Does the VRT possibly also affect the cells that have 4 millisecond retention time?
Yeah, absolutely. That's why I believe, that's why this is very difficult. It's very difficult, in my opinion, for the manufacturers to guarantee no cell will fail at 64 milliseconds today. They have to be able to do everything that I just discussed, right? Data pattern dependence, variable retention time, and they are not under control. They don't have full control, as you can see over here. So my feeling is that there may be some DRAM failures that are being caused because of some cells that are sometimes jumping across that 64 millisecond line. It's possible. It's very hard to isolate those it's possible. And it also probably happens at high temperatures, right? Because all of these 64 millisecond specifications are done at high temperatures. Well, actually, maybe I should say it in a different way. 64 milliseconds is low temperatures, 32 milliseconds is high temperatures when we actually did this. So high temperatures is where VRT becomes more likely, and retention becomes even bigger problem, basically. Okay, so this is a paper that analyzed all of that actually, and I would recommend, I think this is also one of the recommended papers if you're interested looking at it. So after we wrote the radar paper saying, okay, there's great potential, we said, let's dig deeper. These are the problems actually you need to solve to make it work. And this paper did not provide solutions, it provided directions, and later papers actually provide some solutions. Okay, so basically, how can we reliably find the retention time of all DRAM cells so that we can make DRAM more reliable and secure? Basically, even if you don't want to reduce refreshes, I think this is important so that you can actually really understand whether you're refreshing, whether refreshing at 64 milliseconds is a good thing to do, or should you refresh more frequently for complete security and reliability. In fact, I don't know if DRAM is, if there are some cells that are consistently jumping between basically consistently jumping from this line of 64 milliseconds, potentially that could be exploited as a security vulnerability, right? It's not as nice as RowHammer, clearly. RowHammer, you can write a program that causes bit flips easily. But with retention time, if you can somehow identify those cells that consistently fail because you're not refreshing them enough, just because of variable retention time, for example, you can potentially monitor them and you can do a security attack. I think this could be possible, assuming those cells exist, but it requires more work. That's why that's what this means, basically, making DRAM more secure. And of course, making techniques like radar work to actually get rid of the refreshes requires you to really understand the retention failures and retention times to improve performance and energy and quality of service. So I'm not going to go over all of these works. There's been a lot of work. A lot of work is from my group also to really mitigate the retention issues. This work, for example, looks at different error mitigation techniques. It quantifies this variable retention time phenomenon even more. It looks at how you should actually, the strength of the, it talks about error profiling in the presence of ECC, how strong your ECC should be, how much online profiling you should do, etc. It's very interesting, I think. This work proposed a solution for actually tackling the variable retention time problem. And this is, I think, the state-of-the-art solution, except for the Reaper paper, which I will also briefly mention. This is the work that I mentioned. If you really want to understand the mapping of the cells, you should really look at this work. This talks about the data-dependent failures. And this takes advantage of the content of the DRAM cells. I think somebody mentioned, for example, if you have zeros, don't refresh it, right? And this is kind of a similar idea. If the content doesn't change, maybe you don't need to refresh it once in a while, but you need to read the paper for more ideas. This work actually looks at profiling, provides a profiling mechanism to robustly profile and in a fast way. Again, I'm not going to go into details of these ideas. Since we do that, then we will cover the entire lecture. Well, maybe multiple lectures. And then if you actually have modern manufacturers start putting ECC error correcting codes inside the DRAM today. And this complicates your error profiling also. Because now you have internally some error correction mechanism that's happening inside DRAM. And if you're profiling for errors in the memory controller, well, you have no idea whether the errors are being corrected by this mechanism or not, right? Or whether the errors are induced by this mechanism or not. Because internally you have some error protection, okay, error correction. You reduce the retention, you reduce the refresh interval. You want to see whether the row actually can maintain data, right? Internal error correction mechanism may correct the error that you would otherwise see. Okay, that's one option. But internal error correction mechanism actually may lead to errors also. If it cannot correct, it can actually lead to more errors because it gives you data that has more errors than actually there are because it tried to correct, but it couldn't correct because of the way it works. And as a result, this really complicates your understanding of the retention failures. You cannot have nice curves like what I showed you. Actually, I didn't show you all those curves, but you would get nice curves in terms of retention time profiles. Actually, I showed you one curve, right? that was like this, right? As you increase the refresh interval, you get a curve like this. And that's very consistent across many, many DRAM chips. If you do it on a chip that is internally correcting errors, that curve becomes more rough, basically. So your understanding of the errors become much more limited and let's say disrupted, if you will, if the chip internally does some things. Yeah, and this paper actually talks about that. This paper tries to reverse engineer. Actually, both of these papers try to reverse engineer, and they're successful at that. And this is an upcoming paper that actually proposed a profile mechanism to improve the reliability as well. But I'm not going to talk about these. Now, let me, in the given time, talk about these Bloom filters, because many of you said you don't know about it, right? Unless there are questions in the previous part. So I would recommend looking at these papers that are interesting. Clearly, it's a lot of papers, but you can see that this is a decade of research that has led to more and more understanding of what's going on. Okay, let's talk about Bloom filters. So binning, basically. How do you efficiently and scalably store rows into retention time bins? And we're going to use this paper by Bloom from 1970. And that's the idea. So what's a Bloom filter? Since many of you don't know it, basically it's a data structure. It could be implemented in software or hardware. Any data structure can be implemented in software or hardware. Of course, there's a trade-off, right? But this is a probabilistic data structure, and its purpose is to represent set membership, meaning your input is an address of an element, and the data structure says it's present in the set or it's not present in the set. That's your output. It's very simple. So basically, it represents presence or absence of an element in a set. Make sense? So it's probabilistic, meaning it's representing set members in an approximate manner. So if you want to represent set membership in a non-approximate manner, in an exact manner, let's say, you can use 1 bit per element to indicate absence or presence of each element from an element space of n elements, right? So n elements, in this case, let me be more practical, say rows. Actually, maybe we should also use this, and we can try how to use this. Can people see me? Yeah, on Zoom, I guess. What do I need to do to use that? I guess I turn this off. Yeah, let's use this white one. So basically, if you want to be non-approximate, you can think, I like thinking visually. So this is basically a bit vector. And if you have, I don't know, 8 million rows, basically you have 8 million bits, 1 bit per each row, saying it needs to be refreshed every 64 milliseconds. It doesn't need to be refreshed every 64 milliseconds. So you have 2 bins in this case, right? Well, I guess maybe the bins could be, well, I guess one may mean refresh every 64 milliseconds. I guess the other, I don't like this. Why do I not like this? Because you need to know how often to refresh the other one. The second bin may be refresh every 256 milliseconds, right? I get rid of the 128 bin basically. Make sense? So if you want 2 bins, well, 1 means refresh every 64 milliseconds, 0 means refresh every 256 milliseconds. And your profiling would set these bits, right? But this is costly, of course. 8 million is just an approximate number, right? This could be 64 million, depending on how many rows you have. And in the future, it's going to be even more, right? So you don't want to spend 1 bit per row. But if you want to be exact, this is what you spend. And this needs to be stored in the memory controller. So you don't want 64 million bits in your memory controller. This also needs to be written to your non-volatile storage so that it can be fetched into the memory controller. You need to think about system level issues. So what we're going to do is reduce the size of the bit vector to much smaller. You'll see the size, and make it approximate so that this can be stored more easily in the memory controller. Let's say 1K. I can deal with 1,000 bits in my memory controller, right? And that's what this is basically. Now we have approximate set membership. We use this much smaller number of bits and indicate each element's presence and absence with a subset of these bits. Now the question is, of course, how do you indicate that? Now, because clearly you cannot have exact information, you have 8 million rows. Here you have 1,000 bits. You need to have a mapping function from the row address to the bits over here, bits from 0 to 1023, right? So you need to take the row address with my terrible writing. If it's 8 million, this is 13 bits, right? Is that correct? No, it's 23 bits. And you need to map it to, using a hash function, let's say. What is this? 10 bits. Make sense? And that's the idea of Bloom filter, basically. It's the simplest idea, basically. You take an address, element address, map it to bits. So for example, if row 0 is supposed to be refreshed every 64 milliseconds, the address 0 through the hash function gets mapped to some bits, and that bit needs to be set now. Some other row may get mapped to the same bits, right? And that should not be refreshed every 64 milliseconds. That should be 0. But too bad. It maps to the same bits. You need to refresh every 64 milliseconds, even though you should not. Right? But that's okay. You don't lose correctness because of that. So it's never the case that when you set a bit, you set it incorrectly in the sense that you refresh a row less frequently than it needs to be refreshed. That's the whole point. Basically, you don't get false negatives. So we will see that. So okay, there are 3 operations. You need to insert an address here. You need to test, and you need to remove all elements. Okay, let me give you. Well, I guess you don't see it. Sorry. So maybe I should go back here. I think I should switch here. I don't know how the board is visible to people who are watching it. Can someone give feedback? Maybe they're already asleep.
We see it. We see it. Yeah.
Oh, you can see the board easily?
Yeah, yeah.
Yeah, I think it's better if you actually make it bigger. Yeah, but maybe this is better. Next time I'll try to use this. Okay, so basically this is what I described. We have an approximate set membership, and there are 3 operations you can do on the Bloom filter. This is called the Bloom filter, basically. Insert, test, and remove all elements. Now let me give you the pictorial view on the slide. So normally, so this may be the bin for 64 milliseconds, basically. You insert row 1, saying that row 1 needs to be refreshed every 64 milliseconds. And this is a more, let's say, better Bloom filter. Instead of using one hash function to be able to insert an element into the Bloom filter, you use 3 hash functions. And all 3 bits need to be set for you to deem that that element is inserted into the Bloom filter. So for example, we deem row 1 needs to be inserted into the bin, meaning it needs to be refreshed every 64 milliseconds. You go through 3 different hash functions that map to 3 different bits. All of the bits are set. We will see how you test it. Now, if you want to test whether row 1 is present after you construct everything, of course, this is just for illustration purposes. This is what you do. You take the address, you go through the same hash functions, which map to the same bits, because hash functions are not changing, right? And all of these are set. And basically, because all of those are set, you get the answer, yes, row 1 is inserted, which is what you would expect, right? Okay, let's see more examples. We inserted just row 1, and we test row 1's presence. We should get yes, and we do get yes. Let's test row 2's presence. We use another row address. We go through the same hash functions. This time, the first hash function maps to a location that is 0, not set. The second one maps to a location that's 1, that's set by row 1. The third one maps to a location that's at 0. And you AND them all, and you basically deem that the row is not present in the Bloom filter. The row was not inserted basically correctly. Even though one of the hash functions mapped to a place that is 1, because you have multiple hash functions, you're trying to increase your confidence and make sure that you don't get false positives. I will define false positives, but I think you guessed what that false positive is, right? Basically, you get a 1 even though you never inserted the address into the Bloom filter. You should not get that if you don't have a false positive. Okay, let's insert another row. You insert row 4. Basically, you go through the 3 hash functions. You set 3 other bits. That's good. Basically, you need to insert all of the row addresses that need to be refreshed every 64 milliseconds to this bin, to this bit vector, Bloom filter. At some point, all of your bits may be 1. Then that's bad, right? Hopefully, that will not be the case. because you have very few rows that need to be refreshed every 64 milliseconds based on the picture that I showed you earlier, right? Let's assume that now we test for row 5. Is row 5 present? We go through the hash functions of the address, and it turns out all of them map to 1, and the Bloom filter says, yes, it's present. But recall that we never inserted row 5. We inserted row 1, it set some bits. We inserted row 4, it set some bits. We never inserted row 5. But because it mapped to those bits that were set by other rows that were inserted, the Bloom filter thinks that we also inserted row 5. This is because we just don't have enough bits to represent the information, right? This is the approximate part. As a result, we get a false positive. But again, from our perspective as the memory controller, this is okay. We just refresh some rows more frequently than they need to be refreshed. And as long as we can keep this number under check, we can still get good benefits out of the idea, right? Okay, so that's the idea of Bloom filters. And this is another paper that I mentioned that is extra credit if you're interested in doing it. I like how it's described basically. It's different. It's written in a different language basically, as you can see. Maybe I should read it. But 2 new hash coding methods are examined and compared with a particular conventional hash coding method. Yeah, it talks about the issue as hash coding, but now that you have the context, you will understand the paper much better, let's say. Okay, I should also say that, yeah, in such applications, yeah. Okay, I'm not going to read this right now since we don't have a lot of time. Okay, so what are the advantages and disadvantages? I will encourage you to read the paper though. So clearly, Bloom filters are a good data structure. I'm now talking about just the Bloom filters, not their use and refresh. But I think all of these advantages and disadvantages apply to refresh as well. So Bloom filters enable storage efficient representation of set membership. When you read the paper, you will also get that. I rephrased a lot of things. Insertion and testing for set membership are very fast. You just do hashing and then access of a bit vector, hopefully a small bit vector. No false negatives, meaning if the Bloom filter says an element is not present in the set, the element must not have been inserted. And this is absolutely true based on the operation that I described, meaning that you will never refresh a row less frequently than it needs to be refreshed, right? Assuming your retention time profiles are correct. And that's what we need. It enables trade-offs now between time, storage efficiency, and false positive rate via sizing. You can size the Bloom filter, you can change the hash functions, and that enables trade-offs nicely, and that paper talks about that. But of course, it has disadvantages, which is false positives. An element may be deemed to be present in the set by the Bloom filter, but it may never have been inserted. And we saw an example of that earlier, right, with row 5. So it's clearly not the right data structure to use when your application cannot tolerate false positives. But our application in this case, the memory controller, can tolerate false positives in this Bloom filter. It just refreshes more often than needed. Okay, so basically, this is what I said. Refresh some rows more frequently than needed when you get a false positive, not a problem. Well, not a correctness problem. It's a problem in the sense that you missed the opportunity to reduce a refresh, right, on that row. But that's how life is. It's a trade-off, basically. No false negatives. This is the important part. No correctness problem, basically. It's scalable. This is also important. This is one of the reasons why we chose Bloom filters. A Bloom filter never overflows, unlike a fixed size table. You could have had a fixed size table, right? If you have variable retention time, for example, your table size is 128, and you basically store the addresses of rows that need to be refreshed frequently, let's say 64 milliseconds. You discover during online profiling that, oh, you have one more row that you need to add to the table. How do you add it if your table is fixed size? You need to over-provision the size of the table. That's one option, but you may always overflow if you keep adding rows dynamically. So Bloom filter doesn't have that advantage. It's very easy to set the bits. You keep adding, basically you keep adding more rows by just setting bits going through the hash functions, as opposed to requiring more storage. I think that's the beauty of a Bloom filter. You don't need more storage. Actually, this is another issue. A Bloom filter, if you have a fixed size table and if you add another DRAM module into your system, well, you need to either size your table so that it covers for the possibility of all the maximum size of memory you can have in your system. That's going to be large. Or you need to use Bloom filters, let's say. Or you have correctness issues. Okay, as I discussed, there's no need to store information on a per row basis. In this case, simple hardware. And we get away with only 1.25 kilobytes for 2 filters. in my opinion, we could actually have done one filter. In fact, we have 2 filters for a 32 gigabyte DRAM system. So it's very efficient. And I think it's good for you to think about bloom filters. Again, in hardware or software, these are very useful data structures. And whenever you can tolerate false positives. And there are other examples of this. Radar paper is an example, but there are other very good examples of this if you're interested for caching purposes. Okay, let me quickly finish the radar part. Basically, refreshing is easier, actually. I'm not going to spend a lot of time on it, but basically, the memory controller checks the bins and decides whether or not to refresh a row. So you keep the way it works is you keep generating addresses that come up for refresh. An address comes up for refresh. You check the bin, and if it's not its turn to be refreshed based on the bin's contents, then you don't refresh it at that point in time. Okay, and you can implement it inside the DRAM or the controller. But I think maybe this is a good time to stop. I've already discussed, actually, very quickly. In the paper, we proposed to implement in the memory controller, but you could potentially implement radar inside the DRAM as well. There are different trade-offs that we will maybe cover when we go to DRAM design. Okay, maybe this is where we should stop, basically. Where else do you, I think we've discussed a lot, but it's good to keep thinking about this. What else can you do to reduce the impact of refresh? What else can you do if you know the retention times of rows? And how can you accurately measure the retention time of rows? And I'd recommend reading this experimental analysis paper, which I mentioned earlier as well. Should we summarize, or? I think we're already out of time, but let me summarize quickly. Basically, it's a critical challenge, as I mentioned. There's several promising solutions. Eliminating unnecessary refresh is one. Reducing refresh rate with online profiling and detecting, correcting any errors is one. Which we did not discuss what parallelizing refreshes with accesses. That's also important. This requires some changes to DRAM architecture. And clearly, we've discussed the retention time behavior. And there are works that enable realistic variable retention time aware refresh techniques. And I believe there are many avenues for overcoming DRAM refresh challenges. There's still more to do, in my opinion. Although I think the, let's say, low-hanging fruit, which was not that low-hanging, is gone, let's say. I think you need to think very much out of the box and differently to get rid of refresh. But I still see ideas, actually, that can be quite good. For example, you can exploit application behavior, right? Like we discussed. If you can do it in a good way, maybe you can actually get rid of refreshes by writing your software in a different way. And this is a parallelizing refresh and accesses paper. Okay, this is just to mention that industry was right. The paper that I mentioned yesterday talks about refresh as a key scaling challenge over here and variable retention time as a key scaling challenge. And I don't remember if we actually have this in the homework also, but I would recommend reading it. If not in this homework, we'll have it as an extra credit in the next homework. And I think this is where I will stop. Basically, we will dig deeper like this in this course. We'll see more. And if you have any ideas based on what we discussed, feel free to discuss it. We had a good discussion today. Okay, I don't want to keep you here longer. If there are no burning questions, if you ask the burning question, let me know. If not, have a good weekend. I will see you next week. Take care. You have a question?
I do have.
Feel free to go if you need to go.
It's a
There's one
question.
Yeah.
It's about the. So we are currently registering for the exams, but your
okay.
registration page, I couldn't see the.
Yeah. So the exam for this course is going to be during the session, meaning it's likely going to be during the last week of the semester.
There's no registration.
Yeah, there's no. Well, there's no registration. Yeah, there should be no registration. Yes. Yeah, that's a good question. Okay. Yeah, sure. Go ahead.
So it is refresh, and like so refresh, I guess, is also like pretty much the issue of reliability. It's scaling, I guess. But, is that the main reason why hybrid memory is motivated? Because like that, if it's hybrid, and you can have memory that can tolerate like only like a 97% correctness rate, you can like arbitrarily essentially scale your DRAM while not refreshing at all.
Yeah. I think that's one. That's not the main motivation, I should say, but that's one benefit of hybrid memory. Some part of your memory doesn't need refresh. Some part of your memory needs refresh. And you can reduce your DRAM size based on the application behavior, right?
Right. I don't. It's like I remember like it was listed that efficiency of hybrid memory.
Yeah.
How by what other mechanisms? Efficiency?
Could you say it again?
How else is the efficiency increased then for hybrid mechanisms? Because a hybrid between PCM and DRAM, I don't see how that increases efficiency other than by decreasing the
refresh burden. Yeah, certainly. I think that's the main. But there's another efficiency part, which is phase change memory is non-volatile, right? It improves system level efficiency if you can manipulate persistent data directly in phase change memory. You don't need to store it to SSD, which is much slower and much more inefficient, let's say. So that's another way where phase change memory can enable efficiency.
Oh, I see.
Yeah.
Okay, cool. Okay.
Makes sense? Okay, cool. Okay, I don't know what's going on here.